Let's see, can you see my slides? Sorry, just give me 1 second. A window, this window, share. I can't share the screen. Permission.
You know, we need permissions for you to share.
I think you need permissions. Oh, maybe I need to set permissions on my hand. Sorry, give me 1 second.
No problem.
In the meantime, yeah, I can, of course, fill you in on the positions the one that I could not remember rightfully, because I do have a fair number of connections with Rubin. So I've been the science collaborations coordinator for...
Oh, she left.
Don't worry, I think it's the correct path. I mean, when she's giving the permissions, has to reload the browser, and I think it is a good sign.
Okay.
She should enter automatically again. Yeah. Okay.
Where? Hopefully things are gonna get smoother as we go. I've been the science collaborations coordinator for the 8 science collaborations. That's an organization that includes about 2,000 members for about 5 to 6 years now, and the chair of the Transcendence and Variable Star Science Collaboration for just a bit over that amount of time. I'm actually the outgoing science collaborations coordinator, and now you should be seeing my slides, I'm hoping.
Yes.
All right. Do you see an infinity mirror? I'm getting a warning about the infinity mirror.
No.
I'm assuming that it's fine, and I'm going to go on.
Only the presentation we see.
All right, awesome. So right now, I actually am the deputy project scientist for Rubin Observatory Construction Project. This is the title that I gained just recently, and I am the outgoing science collaborations coordinator. If you're a science collaboration member, you voted hopefully in the election, and today you will hear who the new science collaboration coordinator will be after me. I want to start with a quick acknowledgement of the land, because most of the work that I will talk about is done at the University of Delaware. The University of Delaware has worked with the local Native American tribes on a land acknowledgement, which you can see here in the screen. I'm not going to read all of it in the interest of time, but just the beginning and the end. The University of Delaware occupies a land that is vital for the web of life of the Lenni, Lenape, and Anticoke, who share their ancestry, history, and future in this region. UD has financially benefited from this regional occupation, as well as from indigenous territories that were expropriated through the United States land grant system. While the harms to indigenous people and their homelands are beyond repair, we commit to building right relationships going forward by collaborating with tribal leaders on actionable institutional steps. The first one of them is the delivery of this acknowledgement every time we talk about the work that we do at UD. So I'm primarily a time domain astrophysicist, and I was asked to talk primarily about time domain astronomy. So that's what I will do. We'll talk about this plot and how Rubin fits into this plot, and also how my research group fits into the same plot. I will tell you what Rubin is and its legacy survey of space and time. And I will talk about a few projects that myself and the students and postdocs in my group are doing that are related to Rubin. There's a lot going on, and I have the fortune to working with a large number of great students and postdocs, and I won't be able to mention all of them, but just a couple of their projects and a couple of the people. But I do want to acknowledge that there is a lot more going on with a lot of great people. And if I can, I will try also to connect this work with interdisciplinary work that I do outside of astrophysics. Probably the only thing that I will get to is to talk about light pollution and how we can probe light, I will talk about pollution in the air and how we can probe pollution in the air by ways that are similar to ways in which we study some astrophysical phenomena, particularly with Rubin. And if I can, I will also give you some sound clips. I don't know how they're going to work on this video platform, but I'll try to give you some sound clips of some renditions of the Rubin data as work that we are doing both within TVS and within my group to make the Rubin data more accessible to a broader audience. So let's begin with time domain astronomy in general. So I find it fascinating that for thousands of years, humans have been extremely curious about the sky and literally studying the sky. We can argue that science has arisen from the study of astrophysics, but the sky had been interpreted for that entire time as an immutable static object, which also perhaps gave comfort to people to think that there was something so constant in their lives. And in fact, that couldn't be further from the truth. We know now that there are tremendous changes that happen in the night sky continuously. I'm using this slide of the sky over Chile, the sky over the site, a site nearby, the one where the Rubin Observatory is being built. This is a slide that I'm stealing from Andy Connolly's TED Talk, and it shows the beautiful sky above Chile as well as what we don't see. The explosions of supernova that are happening at a rate of 10 supernovae per second somewhere in the universe. Of course, most of them are too faint for us to see with the naked eye, and even with some of the most advanced telescopes. And Rubin will bring to light literally a lot more of these objects. I also have a sound clip that will give you another perception of how this supernova explosion will manifest if we could hear them instead of seeing them. I don't know how that rendered over the connection, but it sounds a bit like popcorn exploding in the sky. So that's a pictorial vision of the time domain sky. This is a more scientific vision of the time domain sky. So the way in which time domain astronomers like to describe the ever-evolving sky with all of its transients that are described by characteristic time scales of the change and brightness, and this is absolute brightness of the objects. And so there's a lot of things to notice in the sky, but particularly the extent of the x-axis is very significant. This is a logarithmic scale in days. So it goes from fractions of seconds to decades. This is 10 to the 2 days. So we're at about 10 years here. And a lot of the regions of this diagram are populated, but particularly this region here at roughly daytime scales to tens of days, maybe fraction of days starts to being a little bit more sparsely populated. And if we had seen this plot, not now, but just 50 or 100 years ago, it would have looked a lot different. It would have looked pretty much only like this until about a few decades into the 1900s. So all that we have learned about the night sky, we have learned essentially since then, and we've been able to disentangle the existence of many phenomena that have different time scales and different brightnesses. And I have a couple of things that I want to point out. These time scales are the easier to access. So the time scale of roughly 1 per day or once every few days. Those are time scales that are also going to be really easy for Rubin to probe. But Rubin Rubin LSST is a survey that will extend all the way to 10 years. So it will be able to probe the time scales that are longer than months and years, all the way to a decade, quite in a way that is unprecedented that level of systematic exploration anyways. And then an important question is, how can it probe the time scales that are so hard to probe such that this region of the diagram is largely empty? It's possible that nature has decided not to put really anything in electromagnetic wavelengths corresponding to the optical wavelengths at these time scales. It's in fact hard to produce phenomena that evolve at sub-second time scales in the optical, but it's also true that we do have an observational bias against being able to learn about those regions of the space. So it's a big question whether this gap is filled, and we just don't know that it's filled, and how can Rubin help us fill it? Particularly related to that, some of the work that I want to highlight from my group, Xiaolong Li, Fabio Ragosa, Will Clarkson, and myself have been working in the context of the Rubin observing strategy work, which I will mention in a minute. So if that doesn't make sense to you, don't worry about that yet. We've been working on trying to assess how well Rubin will be able to detect entirely unknown phenomena that we have neither observed before nor that we have conceptualized. And that includes those very hard time scales to probe. So let me tell you finally what is Rubin Observatory and LSST, those two words that I've mentioned throughout. So, and why I think that Rubin Observatory can usher a new era for time domain astronomy. So Rubin Observatory refers to the observatory, so the physical facility, the people that work for Rubin, as well as the infrastructure that will produce and distribute data from the observatory. And LSST refers to the legacy survey of space and time, the survey that Rubin will engage in the first 10 years of its life. This survey is designed in a very specific and deliberate way to be able to be transformational in 4 areas of science. I'm going to mention these areas of science, but I want to give a specific qualifier to what I'm going to say. This does not mean that Rubin won't be transformational in other areas of science. The reason why 4 pillars of science, such as the ones that I'm going to describe, have been chosen is because they're different enough that they stretch the technical capabilities of a survey to an extent that pretty much ensures that this survey can make a mark in any domain of astrophysics. So the 4 areas that have guided the design of the survey, the 4 aspirational goals that Rubin has committed to, are to probing dark energy and dark matter through exquisite measurements of many probes, including strong and weak lensing and large-scale structure, mapping the Milky Way and local volume with resolved stellar population, and this will amount to about 17 billions of stars, characterized in color, variability, and building an unprecedented inventory of the solar system that will go from near-Earth asteroids, potentially hazardous to our life, all the way to the distant Oort cloud. This will include 6 million bodies that will be cataloged in orbit, and then the theme that is dearest to my heart and perhaps to yours, exploring the transient and variable universe. Rubin will produce 10 million alerts every night that will be shared worldwide with no proprietary restrictions. An alert is a notification of something that has changed in the night sky compared to the way in which we are used to see it, which is represented by what we call a template, a high fidelity image of that very portion of the sky. So anything that changes in that portion of the sky by more than 5 sigma is going to be called an alert and shared with the world. And it should be noted that these alerts will be shared 60 seconds after observation with a really impressive technical feat. But I want to point out that all of these 4 areas, even though one is literally dedicated to exploring the transient optical sky and the variable optical sky, really all these 4 areas do connect to time domain astronomy. Just some simple ways in which they do, even though that's even an incomplete picture. Dark energy and dark matter, one of the chief probes of dark energy is supernova. Now there is also gravitational waves that help us and that really help us understand cosmology at large, or have the potential to, and are also time domain phenomena. Mapping the Milky Way will do so through stellar objects, and the majority of stellar objects has some form of variability. One can argue that all of the solar system objects are variables in that they're moving around the sky, but they're also intrinsically variable. And some of the specific objects that have known variability are comets, etc., etc. I have some information about the survey that will help us understand the data that I will describe in a minute. So the single image depth for the survey is about 24. The images are collected in 6 filters, and so each filter has its own depth limit, but you can use 24 as a guiding number. And once you co-add the 10 years of data into a deep stack, the stack will reach a magnitude limit in excess of 26. This is a really significant depth. You can think a little bit about it as maybe the depth that Hubble Space Telescope's images reach, but we will have them for the entire southern hemisphere sky. This is not exactly a fair comparison because this is a ground-based observatory, so the image quality will be impacted by the fact that we live on Earth and we have an atmosphere to deal with. But the depth of the images will be similar to that of the beautiful HST images that you are accustomed to, but we'll have that for the entire southern hemisphere sky instead of some very small and selected fractions of the sky. Over 10 years, it will collect over 800 images in each position over the southern hemisphere sky, and with some fields, specifically 5 deep drilling fields, being observed at a higher cadence with even more images than that. And I'll have some maps to show the depth as a function of the position in the sky in a minute. This is achieved through a telescope, which is an 8-meter telescope. It's a very peculiar telescope in shape. It's a little unusual to see a telescope being this sort of compact and chubby. The reason for that is that to be able to observe such large fraction of the sky so rapidly that you can collect a full 18,000 square degrees, so the full southern hemisphere sky, observe it once every couple of days, and in fact with twice at least two images at least every night, you need an extremely large field of view, but also an extremely good image quality. So the 8-meter telescope, LSST telescope, sits here in this diagram of famous and large US and European facilities. US, European, and Southern American facilities, I guess. International facilities. I see some other nationalities represented as well. And it has this peculiar shape with this big hole in the center that I'll tell you about in a second. But it's comparable in size to Gemini, for example, which is also about an 8-meter class diameter telescope. So the big hole that you see in the center that makes the shape of the telescope so peculiar is to host the DOE LSST camera, which is a state-of-the-art optical imaging camera with 3.2 gigapixels. 3.2 gigapixels should be an impressive number in and of itself, but let me give you a more concrete description of what that means to make it even more impressive. It would take 378 4K ultra high definition televisions to display a single LSST image at full resolution. This camera is about the size of a person, about the size of a car. And the field of view that I described, 9.6 square degrees, hosts the moon about 40 times. The camera and the telescope are in the latest stages of construction. Here you can see the telescope in its dome in Cerro Pachón, Chile. Here you can see some more images from the observatory. Here an image of the filter, one of the 6 LSST filters, which are proportionally as big as the camera's field of view, of course, CCD plane, of course. And of course, we had delays that were due to COVID, and the site was vacated in 2020 during the first wave of COVID, and occupancy has been reduced on and off since then, which pushed the original start date planned for 2022 by about 2 years. So we have an expectation that the survey will now start in 2024. And this is a boring chart that describes the latest stages of development and the early stages of operations, which you can look at on your own when you get the link to my slides. What's most impressive about the observatory, at least to me, is the data volume. Rubin will deliver 20 terabytes of data, of imaging data every night. That is a factor of 10 above what's been delivered by precursor surveys, even the largest precursor surveys. So let me give you a sense of what that means. At this level of precision, at this level of depth, everything is blended and everything is moving. So the images that we receive from Rubin are not only very large, but very rich of an enormous amount of information. Let me replay this animation. Let's see if it works. This is an image as we saw of the sky as we saw with the SDSS survey, and this is what we expect a Rubin image of the same portion of the sky would look. And I'm going to do it again with a different image. Here you see a galaxy, and you see the same galaxy revealed by the music survey, which is a survey that is expected to be about 1 magnitude shallower than Rubin. So the richness of the Rubin images is going to be really unprecedented. I'm going to skip a few steps in the interest of time. I need to describe very briefly the data products of Rubin, though. So there's a number of products that the observatory will deliver. The first one are the immediate alerts. So 10 million alerts, about 10 million things that have changed in the night sky will be revealed and distributed in 60 seconds from image collection. This will include a small section of the sky, a postage stamp where you can see the transient happening, as well as characterization of the transient, photometric time series, etc. These data will be distributed through brokers, which are intermediate community softwares that will take the data from Rubin and distribute it to the world. And the rest of the data products are proprietary and accessible to the world 2 years after the proprietary data release. And they include 24-hour releases of the same alerts, which are augmented with improved data reduction, as well as annual releases and annual stacks as well. And also to access and process this data, Rubin will offer computational facilities. You see that here at the bottom, the Rubin Science platform. So in the context of time domain, then, about this plot that we mentioned earlier, where is Rubin actually going to be impactful in this in the study of time domain astrophysics? That is, to some extent, on one end, I want to say it's going to be impactful in almost all time scales, and I'm going to try and describe some ways in which it can be in a minute when I talk about the work of my group. On another hand, I want to say that this is still, to some extent, an open question, because it's a question that concerns survey design, and the survey is being designed as we speak. 800 images for each field and 18,000 square degrees covered to the magnitude that I mentioned earlier. But you can imagine that different science drivers would prefer that within the constraints that I just described, the survey to have different characteristics. For example, some science drivers would prefer the survey to be faster, to collect images at shorter timescales, perhaps at shorter timescales in some portion of the 10 years, to then give way to longer timescales and some other portions of the 10 years. Or some maybe to go deeper as opposed to extend the survey wider. And these requirements are in tension and may favor some science cases over others. And so this becomes an exercise of balancing scientific priorities and the needs of the scientific community, which is being undertaken by Rubin Observatory's SCOC, the Survey Cadence Optimization Committee. And I want to mention it here particularly because for time domain, this is really important. On the left side of this plot, you see different footprints of Rubin. The color corresponds to the depth of the survey at a position in the sky. The yellow dots are the deep drilling fields, the 5 pointings that will be observed at a higher depth. And on the right side, you see across all these images that are being shown in the movie, the distribution of time gaps between observations and how broad it can be. So every point in this distribution represents one potential way to do LSST. And the time gap between observations in the same filter can change quite dramatically between one potential survey approach to another. And which survey approach is going to be chosen will be decided by the end of the year, but it's still an ongoing question. Let me skip over this. And perhaps over this as well. These are just graphical representation of things I've already said. The 5 sigma depths in G-band and R-band will be between 23 and 24 for the whole sky, and a COADE between 26 and 28. But what you see in addition here is the extent of the sky that will be observed, the 18,000 and more square degrees that I mentioned earlier. The time gap in general, you want to think of a survey that has a median inter-night time gap. So between 2 nights, the repeat observations on the same portion of the sky will be about every 3 days, with some positions being observed more rarely, as a high time gap as 15 days at the edge of the survey. And within 1 night, though, there will also be multiple observations, typically spaced by somewhere between 20 minutes and 40 minutes, and there's potential for a 3rd observation in the same night. Another really important characteristic for the survey is the extremely high image quality that leads to an extremely precise astrometric characterization of the sources, and correspondingly a very high ability to measure distances of objects just based on how they look in the images, in the Rubin images, through parallax method and through direct proper motion measures. The comparison here is for a parallax error, so an error on distance just as generated by parallax, that can range but can be as small as a fraction of a milliarc seconds, which is really particularly impressive if you think that Rubin is, like I said, a ground-based survey that will have to deal with the atmosphere, which always degrades the image quality. Let me mention the science collaborations really quickly. This is a diagram of the Rubin ecosystem. You have the construction project right now at the center, and the operation project, which is right now pre-operation. Of course, operation will be at the center soon enough when observations actually start. The science collaboration are these flowery piece of the diagram over here. There are 8 groups. The one that I've been mostly connected with is the Transcendent and Variable Star Science collaboration, but all 8 groups altogether represent different areas of science and different expertise, but are also an extremely interconnected organization, which really establishes a network between the scientists that work within each science collaboration. Altogether, there are over 2,000 people, 25 countries at least are represented, and 6 continents. And the diagram to the left shows the growing size of the science collaboration over the past few years, and the diagram on the right represents the interconnectivity that I mentioned. One of the products of the science collaboration that relates to what I told you were papers that were written in the context of designing the survey strategy for Rubin by each one of the groups. And this diagram shows, again, the interconnectivity of the work that has been ongoing within the science collaboration. This blue art here are the papers that were submitted by the Transcendent and Variable Star Science collaboration. Altogether, there were more than 40 submissions, and 85% of them were led by science collaboration members. But also, if I move my cursor over one of these papers, this in particular about targets of opportunity for observations for gravitational waves, you see that the authors of this paper belong not only to TVS, but to nearly all the other science collaborations. So we work as a really connected organization. Let me skip over this and tell you a little bit about some ongoing research in my working group that relates to Rubin. We call my working group FAST-Lab. We're very proud of the name that we came up with this year. It's Federica's Astrostatistics Lab. There's a number of students and postdocs that work in the lab. A lot of what we do relates to supernovae and explosions, because who doesn't like an explosion? Much less an explosion in the sky. And when you work on supernova and explosion, a lot of what you want to do is you see the explosion, you would like to rewind the tape and be able to tell what is the star that exploded. That, of course, is not so easy, not as easy as it might have looked by this graphic, because for one thing, we cannot rewind time and re-see the progenitor of the explosion. And because the information that we get from an observatory, even Rubin observatory, about an explosion is relatively small, right? So we see something changing in the sky, we can measure its brightness, we can measure its brightness in multiple bands and get colors. Ideally, we can measure the spectrum and the spectral evolution of the transient. But Rubin is a photometric survey, which means that we won't be able to see spectra of the object, the spectrum being the light split by wavelength in small wavelength band. We'll be able to get a photometric light curve, and we'll be able to get this light curve in 6 bands for every object that Rubin detects. A really important element of time domain astronomy in the Rubin era is how do we automate the discovery chain in astronomy. And I see that my co-chair, Rachel Street, has just joined the call, and she's really a protagonist in this part of the Rubin story. So Rubin will function as a discovery engine, and like I mentioned, it will discover 10 million alerts per night. But then these alerts will have to be further studied. And part of that will mean trying to collect spectra for them, or even just trying to collect more photometric information about these objects, or connect them to existing information about that particular location in the sky and the variability of those objects, as was studied by other surveys. And a lot of the work of the community has been towards the automation of this process, which is necessary because of the sheer data volume, 10 million alerts. So as part of that, of the astronomy discovery chain, we had the engine, like currently ongoing ZTF, for example, and upcoming Rubin LSST. We had the community brokers. These are intermediate pieces of software that I've already mentioned that will augment the 10 million alerts and share them with the community. We had the target of observation managers, which will enable picking up a selected subset of these events that are of interest to a scientist and connecting them to the observatory at which the scientist has access for observation. And hopefully this process folds back the data into the target of observation managers and back into the brokers to continuously augment our understanding of all astrophysical phenomena in time domain. I'm going to skip a couple of slides and maybe focus perhaps on this. The picture that you see is the one of a postdoc that works with me, Somaya Habkash. She is also an upcoming Catalyst Fellow. Catalyst Fellowship is a fellowship organized by the LSST Corporation with support of the Templeton Foundation, precisely to establish fellows that will advance Rubin science, and she is one of the members of the inaugural cohort. She's working on templates for unusual supernova subtypes. Particularly, we're thinking about stripped envelope supernovae, which are supernovae that have ejected their outer layers as stars before the explosion. And she's building templates so that we can really solidify what is our knowledge of these objects right now. And once we see a new object, will it be one of the classes that we already know, or will it be a new object, linking us back to being able to discover the unknown with Rubin? So here you see a template that she built with existing data for a particular subtype of supernovae called type 2Bs. You also see overplotted recent observations of ZTF objects from a paper that Hannah Hall wrote. And you can see that there is already new classes of objects that are arising in the existing data that are for now quite sparse. These objects are supernova type 1BN, so narrow-lined 1Bs. This is a sparse class right now. We don't really understand a lot of its physics or a lot of its boundaries, but Rubin will increase the discovery rate of objects like this very significantly enables significant progress in this field, in this domain of science, especially if we are able to push the survey to collect more than 2 images per night. So some other work that my group did is to characterize what is the best plan to collect images in one night to be able to specifically tell apart these rapidly evolving, unusual transients. We wrote a paper a couple of years back in the context of survey strategy design called Presto Color, where we indicated how 3 images in 2 filters in Rubin can really allow us to distinguish past transients early within a single night to then trigger that discovery chain that I talked about and collect information about the objects that would really allow us to unlock its physics. So what you see here in this GIF is a space of how the magnitude changes and how the color is measured for different transients. And the ones that you see in red are the unusual transients that we want to be able to separate from the ones that you see in blue. And what's changing between one frame and the next is the time separation between the images that Rubin would take within the same night. We can really actually turn this into already a classifier that would enable us to tell whether an object is, let's say, usual or unusual, just with the 3 observations within one night that Rubin would take and allow us to collect further information to really understand the nature of the objects. Let me move on to perhaps another topic. I think I'll have time for just maybe 1 or 2. Actually, I think I might have time only for, yes, just briefly mention 2 more projects. So let me mention the difference image, the work that we're doing on difference image analysis. So normally when you see, when you want to detect transients in the sky, you do that by difference image analysis. You build a template of the sky. There is a high fidelity representation of how that portion of the sky looks. And then you have your nightly image, the search image that you collect every night. And you want to compare them to figure out whether they look the same. The way you compare them is you subtract the template from the search and you produce a difference image. And of course, this seems easy, but as you can see, the template and the search are inherently different because the template is this high fidelity image that we have produced by putting together a lot of images of the sky, whereas the search image is whatever it is that you have that night in terms of image quality. And so this often leads to artifacts, like in this case, you see a typical artifact called a dipole, a black portion of the image and a bright portion of the image that is due generally and primarily to misalignment between the template and the search. So a student that worked with me, a student from Colombia, Tatiana Cirocuellar, that worked with me as an intern over the summer and is now coming back to the University of Delaware as a grad student, worked on see if we can suppress this difference image step, which takes an enormous amount of computational power because you have to align and scale the images and potentially warp the images to coincide spatially and in brightness. So that you can actually take a difference that does not have artifacts. So she's taken images and search and template images from the dark energy survey and has tried to classify which ones are genuine artifacts and which ones are what we call bogus. So artifacts of which ones are genuine transients and which ones are bogus or artifacts in the image without going through the difference analysis. And there's a lot of work here that goes on in how she designed the neural network for doing so. But the punchline is that she obtained she was able to design a very similar neural network for doing this process, both with the difference image and without the difference image, with a very small degradation in the accuracy of this process. So this demonstrates that you can do this without the difference imaging. This can save the majority of the time that is spent in astronomy time domain searches in the production of these alerts is in fact spent in the difference image analysis. So this can save a tremendous amount of computational time in these searches. But another thing that she did was looking at what is that each neural network uses to identify the object as genuine or an artifact. And she did that through saliency maps, which are maps of importance of pixels in an image. So here you have an image from one of the original papers about saliency maps, and it tells you what a neural network would use to understand whether this is an image of a dog or something else. And it's pretty obvious when you look at a dog, right? So it would use the nose, the eyes, it would primarily use the face and not the background of the image, etc. But it's not so obvious when you're looking at different images in the context of astrophysics. So she found that when you do have the difference image, as expected, the artificial neural network primarily uses the difference image portion of the triplet of the template, search, and image. But when you subtract the image, the neural network has to do a synoptic observation throughout the entire image and use all the pixels, not only the ones that are focusing on the transient, to really understand the context in which a transient may arise and figure out if it's a real, genuine, or an artifact. And there's a number of saliency maps in our paper, and also an estimate of what is being used by each neural network in each case as a function of whether that was a real transient or a fake transient. We think that this work is impactful because it really has the potential of changing the way in which we do transient detection, but we also just really think that it's really interesting to see how a neural network can engage in this problem in the different scenarios. Let me spend a couple of minutes mentioning one more project. One thing that I want to talk about that is a little bit outside of my domain, but some science that I'm embracing more recently is stellar flares. What they have in common with some of the things that I've talked about is that they're very rapidly evolving phenomena. So stellar flares, like we see them in the suns, they're magnetic reconnection activity that causes rapid brightening of a star that is typically very significant, very significant in magnitude. More recently, stellar flares have evolved, the stellar flare science and understanding has evolved tremendously through surveys like Kepler that have been able to take very dense time series of flares. So here you have a flare observed by Kepler, and you see 200 minutes of the flare with an exquisite time resolution that really allows you to see what is the morphology of the flare in the single Kepler photometric band. Surveys like LSSD and its precursor ZTF, you have a flare in ZTF here, are very different though. They don't have a rapid cadence. If you look at a flare similar to that one with ZTF, you get a few data points. And if you look at it with the flare wide, fast, deep survey, you get one data point. So it's a question of whether Rubin can actually be impactful in this area of science. But look at the color scheme that I have here. I've colored these data points by air mass, and this will become important in a second. So to really exploit the very large volume of flares that Rubin will undoubtedly see in its observations, but be able to do flare science in a very different way than we did before with a single data point per flare, we really had to get a bit creative. And what we're proposing is to use a phenomenon called differential chromatic refraction. We can use this phenomenon with Rubin precisely because of the exquisite image quality that Rubin offers. The phenomenon works like this. When I'm looking at a star through a lot of the atmosphere, its position is going to be changed depending on its color because of simple refraction effects. Blue light refracts differently than red light, which makes it such that an image of the star that is blue would appear in a slightly different position than if the star was red. Slight is very slight here, is a fraction of an arc second. So you really need a survey that is able to measure position to a fraction of an arc second. If you can measure this shift in position from what you would expect, then you can measure the color of the object. And if you can measure the color of the object, or in this case of the transient of the flare, then you can measure the temperature of the flare. So Kepler really helped with the morphology of the flare, but it's a single band survey. So really the next frontier in flare studies is to really connect these to temperature. And Rubin can do that through this differential chromatic refraction phenomenon. So on the left here, you see how you would expect the position of the star to change if its temperature were changing from about 8,000 Kelvin to about 20,000 Kelvin, which is what would happen if a star were flaring. And on the right side, you see whether or not we would be able to see the differential or chromatic refraction, to see this position shift as a function of the temperature and in which photometric bands. And it turns out that with Rubin, we can see in G band, and we'll have, again, hundreds of observations in G band. We can see well beyond the ability to measure the position of the object. We can see this shift in position if the temperature of the star goes from its quiescent temperature to a flare temperature of 10,000 Kelvin, 20,000 Kelvin, or 40,000 Kelvin, all of which are very realistic from flare models. It is 2:20 in my time zone, so I think I am out of time. So I'm going to skip over light echo and also over everything else. And the one thing that I'm going to try and leave you with, I don't know how it will render with sound, but it's a project on sonification of the Rubin data that we have engaged in with a student that worked with me last summer, Sydney Patel, at the University of Delaware, and that now has become a collaboration of the Lincoln University through the support of the Hayes and Simon Foundation with the Lincoln University Music Department. And I want to mention that Lincoln University is a historical Black college and university in Rubin, and a lot of the energy of the science collaborations has been spent on trying to engage community that are traditionally not as involved in astrophysics discovery, such as historically Black colleges and universities. And this project particularly is intended to design ways in which we can render the Rubin transient data through sound so that it can become accessible to the blind and vision impaired community, and also so that we can perceive characteristics of the data that might be different through sound than those that become obvious through visualization. So let me see if I can play this. These are two renditions of a simulated supernova in the Rubin data. And I think that is all the time that I had. And I'm going to stop here.
Okay, thank you, Federica. Thank you for the very nice and interesting talk. So now we are available to take questions. I have one myself. May I?
Of course.
Fed, what are the plans after the 10 years of the official survey? Are there any plans after?
So there is a couple of white papers that have been written about this. So of course that we hope the observatory will live a very long and happy life, well past the 10 years of the survey. So the way you want to think about it is the Rubin Observatory is committed to deliver certain level of science product that will enable the science that I described at the very beginning, the 4 science pillars, to the degree to which we expect in 10 years. After that, really, all bets are off. And I think it is premature to decide what will happen and what should the survey do, simply because my expectation is that Rubin will discover very many new and exciting things and really further our knowledge of phenomena in directions that we can't really predict right now, because it's designed to be that transformational. So it's hard right now to say what should our energy be spent on with this facility in the future. But certainly this remains a pristine state-of-the-art facility right now, and it's unlikely that in 10 years, several of the aspects that make this facility amazing will become obsolete. So it will remain an incredible instrument for additional surveys.
Thank you. Any more questions? Martin, I think, or Mariano? I see you're raising your hand.
I do not hear them.
Can you hear me now?
Yes.
Yes.
Okay. So each single image of LSST will be a combination of 2 or 3 exposures to get rid of cosmic rays and so on, right? Is there?
Well, go ahead.
Yeah, sorry. If it's the case, is there any time domain information that you expect to be able to extract between these very individual 15-second exposures?
So I love answering this question. I love getting this question. So, so the most likely scenario is that all bands but you will collect images in 2 snaps. So you're correct. The visit, the 30-second exposure or visit, will actually be composed of 2 snaps in all bands but you, because in you have a very low, it maximizes the readout noise versus sky noise, because you have such low sky background that you can take a single exposure. I do think that there is information in those timescales. The trick here is that the data management team of Rubin is not charged with doing anything with those in terms of data products. So anything that would want to address the study of those individual snaps, anybody who would want to do that would have to process the images entirely themselves, which is, you know, no small thing because of the enormous data volume and, you know, potential. It will put some strain on data access, but, you know, we have plans for that. We just mentioned the link workshop for software beyond what the data management will produce. And so then there's potential to access those images, and there's potential to extract really interesting information from those timescales that are prohibitive to most observatory, but it's not going to be easy.
Thank you.
Hi, Federica. You hear me?
Hi. Yeah.
I have a question. 10 million of alerts per night is a lot of alerts. It will be classified by the brokers, but and followed up by the ION and the other networks. You have an idea what fraction of it? Of course, it depends on the different types of variability, but some fraction will be observable with the spectroscopic follow-ups.
Oh, do I have an idea what fraction can be
You
followed up?
lost a lot of these alerts or interesting objects that you could find. We have the resources to follow.
No, so we don't. I'm not going to answer what fraction can be followed up, right? Because for one thing, because I really don't know, and it depends a lot on how we design our follow-up. So I don't know what fraction will be followed up. It will be a small fraction, certainly. So there's sort of 2 ways in which I want to answer this question. One is, forget about following up the majority of the alert. Forget about only doing science with what you can follow up. That will be an enormous waste of a vast amount of data. So we really do need to think about how can we optimize our inference into these objects through photometry and through, you know, clever ways to do photometry, such as, for example, differential chromatic refraction, right? And an enormous amount of effort has been put into figuring out how to classify the objects in photometry that we normally do classify primarily in spectroscopy. And Emille Ishida here, who will speak in a few minutes, is a protagonist of that piece of the story, right? With the plastic challenge that really has advanced the state of the art for photometric classification of transients tremendously. You know, photometric classification is not characterization. So along with that, we need to advance our ability and build software and build models that will let us know what the physics is through photometry, just like we're building models that let us know what one object is versus another one through photometry, which is, of course, a harder task because classification is like the easiest one, perhaps, of the machine learning tasks, right? But, you know, we're going there. The science collaborations are going there, and collectively we will move towards that. I expect that we'll sort of get to a state where we where it's normal to have far more discoveries than you can have follow-up. And we will be able to advance our knowledge by rare follow-up, joined with large statistical samples that are known to a much lesser degree that can be anchored to the ones that are followed up.
Thank you so much.
I don't think it was a particularly satisfying answer. But...
Oh, come on. More questions? No? Okay, let's thanks Federica again.
You're very welcome.
And we hope that next time you can visit us in person.
I really hope so.
Thank you. So now our next speaker is Rachel Street. Rachel, are you? I see that you are there.
Hello there. Can you hear me?
Yes, yes, perfectly.
Great.
So, can you hear us okay?
Yes, I can hear you okay. Can I share my screen, perhaps?
Sure.
Perfect. Let me see. I haven't used this particular interface
Platform.
before, but let's try this. Okay, hopefully you should see my slides now.
Yes. So in
Great.
the meanwhile, it's our pleasure to have Rachel Street participating in this small workshop. Rachel works at the Las Cumbres Observatory, and among many other things that she's doing, she's been the co-chair of the Transient and Variable Science Collaboration. She's the person behind the TOM toolkit, a very powerful tool to manage your observations of alerts. And we had the pleasure with Mariano to give a glimpse on that, but it's really, really a big machine to learn. But so Rachel now is going to talk to us about the survey strategy for Rubin Observatory. Thank you.
Thank you very much. And hello, everybody. It's great to be able to join you today, and thanks very much for the opportunity to speak. So, as Juan said, I'd like to discuss the survey strategy for LSST, and I'll describe in more detail the process and the tools we use to determine what that strategy will be. So I'm going to start with an overview of the whole process to give you some background, and I'm going to focus particularly on the survey strategy tools for the galactic plane because that represents the topic that I'm most familiar with. And after that introduction, then I'll demonstrate some of the software that Rubin is using to evaluate the effectiveness of survey strategy for different science cases. But before I go any further, let me thank the many, many people who have contributed to this work, in particular Lynn Jones and Peter Joachim, and I'll tell you more about their work later, and also Federica, whom I'm indebted to, our earlier speaker. So, as you know, Rubin Observatory was designed around 4 extremely broad science goals, ranging from understanding dark energy and dark matter to completing a census of the faint solar system objects. So the challenge we face now is to figure out exactly the sequence of observations that will accomplish all of those goals night after night for 10 years. And clearly this question is one of the most essential decisions regarding the success of the ultimate survey. At this point, it's important to acknowledge that some of the requirements for different science goals are inevitably going to be in tension. To give just one example, much of the cosmology demands that we concentrate observations on extragalactic targets at high galactic latitudes, whereas most stellar variables are found in the plane of the Milky Way. So it's often said that the process of deciding Rubin survey strategy is less about optimization than it is about minimizing unhappiness. So clearly, eventually, somebody somewhere is going to have to make some decisions about the trade-offs necessary, and that responsibility lies with Rubin's Survey Cadence Optimization Committee, or the SCOC for short. This is a 12-member panel chaired by Federica Bianco, and they have expertise in all of the different science disciplines of the Rubin science collaborations, and it also includes Lynn Jones from the project's survey simulations team. And there's more information about this committee at the website indicated, where you can find all their reports. I thought it was also worth mentioning the overall timeline for the committee's deliberations. They have held 2 workshops so far to help gather input from the community, and the last of which was held in 2021. And based on what they learned from they published their recommendations for the first phase of survey strategy experiments, which are currently being analyzed. And I'll say more about those shortly. The expectation is that as we go through 2022, the major aspects of the survey strategy will be fixed, and then the committee will focus on the finer detail and optimization. Ultimately, the goal is to be able to implement the determined survey strategy in software for the Rubin Observatory by the 1st of April next year, and that will be 1 year before the start of survey operations. Of course, science moves on over the time that it takes to develop a large project like Rubin, and new opportunities come up. So it's valuable for the project to consult the scientific community at regular intervals to make sure that the scientific goals are up to date and to incorporate new ideas. And one of the functions of the Rubin Science Collaboration is to provide that kind of guidance to the project. So the process of community input to the survey strategy has taken place in several phases over several years, and you can learn more about the whole process on the website linked on the slide. I'll summarize it briefly. The first major phase took place in 2017, when Phil Marshall coordinated a very large team of science collaboration members and composed the Community Observing Strategy Evaluation paper. The following year, LSST announced a call for white papers from the astronomical community, and these were deliberately structured around 7 questions that focused on particularly observational parameters that are needed to achieve the science goals that people wanted to do, such as the survey sky region required, or otherwise known as the footprint, or the limiting magnitude that must be reached. And authors were encouraged to start to design algorithms that could be used to determine whether or not a given strategy actually met its observational criteria or not. Now, there were 46 white papers submitted in total, and they spanned the full range of astronomical topics, and they were often written as collaborative efforts between different science collaborations. It was seen as the community's chance to propose significant changes to the LSST survey strategy, for example, by proposing new deep drilling fields or additional mini-surveys outside the original wide, fast, deep survey footprint. In 2020, a second call for the community was issued in the form of cadence notes, this time increasingly focused on the technical detail of survey observational constraints, and the authors were encouraged to codify that information in the form of algorithms. And most recently, the most recent work on survey strategy has focused on those algorithms, which we also call metrics, which are designed to evaluate how well a given strategy performs for a science goal. And I think it's valuable to explain that process in more detail. So the science idea gathering process has helped the project to document the various observing constraints of the wide range of science that we would like to do with Rubin Observatory. But it's all very well to gather lots of wonderful ideas for the science that we could do. How do we turn that into a sequence of observational pointings and telescope exposures for every night? It's clear that software is going to be needed to take all of those many different observing constraints and combine them into a figure that will sequence the observations on the sky. And to understand how we assess different survey strategies, it helps to understand how that software works. Writing software to decide when and where a telescope should observe is actually quite a challenging problem. If it's a single-purpose facility running just one project, it's not too bad. But most multi-purpose observatories still have humans involved, heavily involved, in the process of deciding what should be observed at any given night. Now, Rubin is a multi-purpose observatory that is serving lots of different science goals, and they wanted to develop software that would determine what the nightly observing sequence should be. And that has the observation that the advantage that when we've written that software, we can then test it. We can simulate how it will behave in advance and then adjust it until we agree that the sequence is as optimal as possible. So the Rubin telescope scheduler decides what to observe in real time. And that has the advantage of making it very adaptable when conditions change, such as, for example, due to weather. To achieve that, it uses a Markov decision process to select the next most important observation to make based on a set of predefined basis functions. Those basis functions describe various observational constraints, such as minimizing telescope slew time, and the system also takes into account current observing conditions, such as weather and the position of the moon. The time-lapse you can see gives an illustration of one possible survey strategy in progress. The colored tiles represent different telescope pointings in different regions of the sky as a function of time, and you can watch the telescope schedule progress through the selection of fields visible at any given moment. The scheduler recognizes 3 different types of fields or sky regions in the survey. The first of these is deep drilling fields. These are mostly single pointings that will be imaged intensively over the 10-year survey in order to reach extremely faint limiting magnitudes. To achieve the very regular sampling that is required for this, these fields receive the highest priority in the scheduler, so that the stage of the scheduler is to check whether any deep drilling fields can be observed first, and whether some of them haven't been observed lately relative to the predefined cadence required. The second type of field are known as the blobs. They really are known as the blobs. These represent groups of telescope pointings that are quite close together on the sky, meaning that they can be observed during the same night, and the telescope doesn't have to spend a lot of time slewing from one field to another. This accounts for the majority of observations in LSST, and the main source of blobs is the region at high galactic latitude known as the Wide Fast Deep Survey. However, there are additional blobs under consideration for so-called mini-surveys of other regions of interest, including the galactic plane, the North Ecliptic Spur, and the Southern Celestial Pole. So the scheduler decides which blob to pick for each night's observations based on whether it's been observed lately, whether it's close to the telescope's current position, which again minimizes time-wasted slewing, and whether it needs observations in one of the filters that is currently loaded to minimize the time spent changing between filters. And in that way, the Wide Fast Deep survey is built up night after night by cycling through the blobs. The last category of field is known as the greedy fields. These are observed only in twilight, and this is a period when no observations of the deep drilling fields or the blobs are allowed. And in this mode, the scheduler selects a field as it does for Tier 2, but it makes no effort to group them spatially. It instead observes a single field at a time, and that's done because the twilight period is relatively short. And twilight observations are also only made in the redder band passes due to the sky brightness. So using Rubin's telescope scheduling software, we can now simulate the LSST survey in operation and try out different strategies and constraints to see what works best for different science goals. With that in mind, Rubin have developed a sophisticated software package for simulating the survey in operation, written by Lynn Jones and Peter Joachim. The simulator takes in definitions of the survey fields together with realistic models of the telescope operations. That includes things like the rate of slew, camera readout time, etc., and the observing conditions at the Rubin site, including data on weather, seeing patterns, and sky brightness. And the simulation makes reasonable assumptions for things like technical downtime for telescope maintenance. That information is then fed to the scheduler as if the survey were in operation, and the scheduler follows its decision process based on a set of predefined basis functions. Different survey strategies can be explored by adjusting those basis functions. And what we get out of this is a sequence of the observations that LSST would consist of, which we call an OPSIM, or operational simulation. So we can now take that output and apply algorithms to it to evaluate how well this particular sequence of observations performs for different science cases. And those algorithms are known as the metrics, and they're based on the algorithms that were defined by the different science cases from the white papers and the cadence notes. Metrics are the algorithms that usually define some kind of statistical measure that we use to evaluate a given survey strategy simulation and determine how well or how poorly it performs for different science goals. The metrics available form into two broad categories. There are quite a number of technical metrics written by Rubin project itself, which were designed to evaluate survey characteristics like the total number of visits to each field over the lifetime of LSST, or to estimate the limiting magnitude reached in a deep co-added frame. The other category is the science metrics, which measure criteria that are essential to different science goals. And that's where input from the science collaborations is very important to make sure that we consider the needs of all of the wide range of science that is possible. By design, the metrics need to read in the OPSIM databases and evaluate the sequences of observations. Now, rather than have everybody write their own code for doing this, Lynn and Peter have written a Python library that's designed to perform those functions, which is called the Metrics Analysis Framework, or the MAF. The MAF allows Rubin project's own metrics, of course, and provides a code framework that allows you to run whatever metrics you'd like on many different survey strategy simulations. And it provides a number of built-in plotting tools to help with analyzing the results. Now, of course, no one person is going to be specialist in all of the science that Rubin will do. So rather than have the project write all of the metrics, they invited the science community to contribute additional ones. So for reference, here's an example of one of Rubin's technical metrics. This simply calculates the faintest object that can be detected at the 5 sigma level if you sum up all of the exposures that Rubin will accumulate for a given point in the sky. You can see that it's written as a simple Python class, which inherits the base metric class from the math library. Each metric class has a standardized format with a minimum of 2 methods. Firstly, the init method, which just sets up the metric objects and handles the keyword arguments, and the run method, which contains the actual business logic. And this can be pretty simple, as in this example here. One key concept to be aware of is that when the metrics are run by the math, they receive a selected set of simulated sequence of observations called a data slice. Most commonly, the science metrics are run for a specific point on the sky or heel pixel, and they're run for every heel pixel across the whole of the night sky, each one in turn. And in that case, the data slice will be a Python object containing the observations taken at a given sky position. This software is entirely open source, and you can find it in the project's GitHub repository. Its formal documentation is in the paper that's shown on the screen, and there's a wide range of Jupyter notebooks that are available to demonstrate different metrics in operation and how to do various functions. So these resources are well worth taking a look at, and I believe they are now linked and the documents available on the Discord server. Okay, so now we have the MAF framework for evaluating simulations of alternative survey strategies, and we need to explore the different survey designs. So after reviewing survey strategy proposals from the community white papers, the SCOC outlined a series of phase 1 simulation experiments that should be conducted in order to explore the pros and cons of a different proposal. Lynn and Peter then ran their simulation software, and they've generated a large set of simulated survey strategy products in the form of SQLite databases. For each simulation, they provide an SQLite OPSIM database which contains the information about the sequence of observations in a realization of a particular strategy, such as what RA and DEC the telescope pointed to at what time, what filter was used, how long the exposure was, etc. They also produce a results database, which contains the values of all the science metrics run by the MAF framework, and a large set of graphics which illustrate the products of those metrics. And you can find all of those data products linked from this page. Okay, so I hope I've given you an introduction to the process of developing the LSST survey strategy and the tools that we have to do it. So for the rest of the talk, I'd like to focus more specifically on some of the contributions to this process by TVS members and finish with a demonstration of actually running a metric. So TVS members have been very active contributors throughout the survey strategy process. When the call for white papers went out in 2018, TVS members contributed no less than 45% of the submissions, and we were co-authors on several more. These papers discussed a wide range of topics covering all of the scientific subgroups, from the extragalactic, such as supernovae and tidal disruption events, to galactic targets such as stellar variability in all forms, microlensing, star clusters, and star-forming regions. There were also a number of papers that focused on methodology, for example, proposing strategies that would reduce aliasing in the measurements of variable periods. There are now metrics available for all of these science goals, and thanks to the effort of many, many TVS contributors and collaborators from other science collaborations, the TVS has a survey strategy task force whose goal it is to coordinate the development of those metrics and to work with Lynn and Peter to get them integrated into the MAF. We completed that goal earlier this year, so that code is available to you. I don't have time to go through all of the metrics, but I did want to give you a flavor of some of the range of the work that's being done, so I'll highlight a few examples. Many of the TVS science groups are working to analyze the survey strategy simulations right now and to see how they impact their particular science. So this is an example from our tidal disruption events group. They've developed a metric to estimate how many TDE events will be recovered for a given survey strategy, and that's shown in these radial plots. The different colored lines represent different survey strategy simulations, which allows the group to compare the number of events that would be detected and thereby identify the most beneficial survey design. Our eruptive variables group has also been particularly active in evaluating the survey strategy. They submitted a proposal for a microsurvey that would obtain high cadence photometry of young stars in star-forming regions, and are currently assessing the different simulations to determine how well they would characterize the variability of this class of object. Rubin's Observatory, extraordinary combination of this very, very wide field of view and faint limiting magnitude make it really ideal to search for the optical counterparts to gravitational wave detections. And TVS members have been exploring the scientific potential of this, of just a few target of opportunity observations from Rubin per year. And this was described in a recent paper led by Igor Andreoni. In fact, there are a number of papers on the impact of LSST survey strategy on various branches of astronomy, and Federica arranged for them all to be published in excuse me, a special edition of the Astrophysical Journal Letters. The first paper in this special edition, led by Federica, gives a really great overview to the whole survey strategy process. I do want to emphasize that the survey strategy research is still very much ongoing and more contributions are encouraged. There's no fixed deadline for contributing papers to this special edition, and the publication charges for science collaboration members are covered by a grant that we're grateful to have received from the Heising-Simons Foundation. So I was asked to speak about the survey strategy for the galactic plane science in particular. So I would like to focus on those metrics, and I'll give a short overview of the approach and then demonstrate how the appropriate metrics are actually run. Now, most metrics are designed to measure a specific scientific quantity. For example, there are metrics to evaluate the number of near-Earth objects that will be detected from a given strategy. And there are also metrics to determine how precisely the dark energy equation of state parameters will be measured. The challenge for galactic science is that it covers such a vast range of science. Dozens of authors contributed white papers on topics ranging from pulsating stars to resolved stellar populations, microlensing, young stellar objects. And all of those authors proposed a large number of metrics for each of those science goals. But what we would really like to come up with is a single guiding figure of merit that would encapsulate the needs of all of these science goals, which would make it a lot easier to compare with some of the other science drivers of LSST. So I approach this problem from the point of view of somebody operating the telescope. And if you're sitting at the telescope and you want to decide how to survey the sky, there are really only a few observable parameters that you can change. You can change the footprint, the region of the sky that you include. You can vary how often you visit that particular field in the sky, or otherwise known as the cadence. And you can decide what filter to use and how often. You can also change the exposure time. This is one of the lesser impacts on galactic science, so I've not considered it here. It does somewhat impact us, and it clearly is, but the survey footprint and the cadence and the filter selection are the most impactful criteria, so I've really focused on those. And I'm deliberately generalizing in this metric to provide a big picture figure of merit as a guide to the SOC. But this is not the only work on metrics for the galactic plane, and it's designed to complement rather than replace the science-specific metrics that I covered earlier. The biggest single influence on how productive LSST would be for galactic plane science is the fraction of time that it spends observing fields in that region of sky. Several white papers advocated for observing the entire galactic plane and the Magellanic Clouds. But a simple back-of-the-envelope calculation will tell you that Rubin can't survey the entire region at the same time as, or the same cadence as, the Wide Fast Deep survey, because it would take so much time that the core science requirements would be compromised. So it's likely that some trade-off will have to be made, and the key question is what regions are most important. So to answer that question, I looked at the white papers that we wrote back in 2018, and I listed out all the regions that the authors identified as being the most important. And I combine them all together, and if you do that, you can plot them on a map of the sky and assign a priority to each heel pix pointing based on how many authors felt that it was significant for their research. So this map includes contributions from many, many authors, and if the region was of interest to more people, it received higher priority. And this clearly identifies some of the most important areas in the galactic plane and the Magellanic Clouds based on the areas of highest density of stars. But in addition to those regions, it assigns weights to other regions of specific scientific interest, such as star clusters and star-forming regions. So that's a good start, but I started to consider what would happen if the SCOC has to make a trade-off between survey area and cadence and has limited time available. So if they can only survey the regions that were of interest to the most people, the highest priority regions, then to take an extreme case, the survey footprint would be much more limited, as shown in this example. So although this covers a lot of science in the bulge and the Magellanic Clouds, it would observe a relatively limited galactic population. And that could compromise some of our other science goals because we would not be able to compare populations along different lines of sight in different evolutionary environments. So I proposed a slightly modified survey footprint to make sure that we cover a different range of sites distributed throughout the galactic plane. I adopted a set of 20 pencil beams. single Rubin pointings, but distributed across galactic longitude at regular intervals to give a better sampling of different populations. Of course, if you naively place 20 fields at a latitude of 0, many of them are going to land in regions of high optical extinction. So I've optimized the placing of those fields according to stellar density, following a suggestion from a microlensing team. And that gives us the revised proposed survey footprint on the right. But for time domain science, you really cannot separate the survey footprint from the survey cadence. Of course, most of our science includes a wide range of time variable phenomena, but from an observational point of view, you can group a lot of diverse variable types into categories that are based on the approximate timescale of their photometric variability. So for example, planetary transits and stellar flares can happen in hours to days. Many pulsation periods are under 10 days, and some microlensing event lasts just a few days, with many other phenomena in that category. As you go to longer timescales, you tend to see different classes of variability, including different ranges of pulsations, disk instability signatures for cataclysmic variables, and at longer timescales still, you get to black hole microlensing and Mira variables. So why those categories in timescale? Because the operational constraint of the telescope and the seasonal target visibility. Now, realistically, the wide, fast, deep survey cadence is on average about 3 days, and longer if you consider data taken in a single filter. So the shortest timescale category is a realistic estimate of the minimum cadence. And most objects in this category are probably going to need additional follow-up to fully characterize them. The other categories reflect the object's seasonal visibility window. Most objects can be observed consistently for about 6 months of the year, although of course that does vary widely. And some rolling cadence strategies would limit observations such that they get observed intensively 1 year, but then no further observations are taken for a gap of months or perhaps years. And so that is another aspect that we need to evaluate in the survey strategy. So I designed a metric rather, to consider the minimum useful interval between observations for different categories of variability. Adopting a very simple guideline from experience, I've assumed that we need to have at least 5 observations within that interval to be realistically able to identify the variable object. And observations outside of that window are still valuable, but they decline in value as the longer the cadence becomes. And the other factor I considered is how long the object is observed consistently for. There are existing metrics for the season length over which an object is consistently observed. So I've used those to evaluate them. There are also additional metrics that are contributed to evaluate the periodicities that can be detected as a result of a set of observations from a given survey strategy. The last aspect of the observational parameters is the filter selection. The 2018 white papers indicated which filters were most important for which science cases. And so I combine those together, gives us a baseline idea of how much time should be spent in each filter as a function of sky position. So this metric evaluates the proportion of time spent per filter at each pointing, summed over the science region of interest. And that compares the ratio of the ideal set of observations to the actual realized set of observations. Okay, so I'd like to finish with a demonstration of these metrics in operation. And before I switch to the Jupyter Notebook, I thought it would be helpful to share a quick summary of where to find MAF resources. As I said, the MAF software is available from the open source Git repository, and it includes a full description of how to install that software on your local machine. The MAF team have also provided a repository of Jupyter Notebooks, which demonstrate how to run the metrics on different survey simulations and describe the metrics in more detail. So they're a great place to start to understand the MAF. And there was also formal documentation of all of the math functions available at the address given there. And last but not least, in order to run the metrics and the math, you will need to download simulations of the LSST operations, the OPSIMs, which you can do from the University of Washington's online database. Now, it's entirely possible to run the math on your local machine, but I thought it would be also helpful to provide the links to the online computing resources, which also provide access to the math. All of these platforms are designed to provide access to large computing cluster facilities through a simple browser interface. The first of these is, of course, the Rubin's own science platform. At the moment, this is available if you join one of the Rubin data previews, but they expect to scale that up to the rest of the community later on. Alternatively, you can open a free account on the NOIRLAB's Astro Data Lab platform, on the Link computing facilities, and also on the Sci server platform. And all of those facilities provide pre-built environments which have the math installed by default. Okay, so I'm going to quit the formal presentation and switch to the terminal. Can you see that okay?
Yes.
Oh, yes, you can.
Sorry.
Great. Okay, just checking. Okay, so the first step is I am going to activate the Conda environment. Move in, and I'm going to make my thing a little bigger, so hopefully you can see that a bit better. So that's activated my Conda environment, and once again you can get instructions on how to install that and get the Conda environment set up on the are available on the install instructions from the math itself. And then I'm going to start the Jupyter notebook, which will trigger in the environment window. Great. And I have a metrics demo notebook prepared. So here we go. So I'm going to demonstrate one particular metric, the galactic plane footprint metric, but the process that I'm going to run through is exactly the same for any other metric for any other science that you would like to do. So hopefully this is a very general purpose of demonstration. So to start off with, in this third cell, you can see that it imports a range of necessary libraries, including the Rubin Sim math library itself. You can see the math is imported here. The metric also makes use of the HealPy library for a number of functions that involve the HealPix map to the sky. And that imported okay, so we'll move on to the configuration. So some of the science metrics are usually calculated for every point in the sky. So we start off by defining the resolution of the HealPix sky map to be used. I've also declared an array of the categories of variability that we will consider. Going back to the description earlier, I considered different categories of variables based on their characteristic timescales, which get compared with the survey cadence. So for the purposes of this demonstration, I'm going to run the footprint metric over the baseline version 2.0 operation simulation. Now, the math provides this convenient get baseline function, which actually generates the default path to that database on your local disk. As a reminder, you can download those databases from the University of Washington. And although this function calls the simulation by default, you can also substitute that path for a different simulation if you want to make a comparison. Okay, so that's imported our database. Now, since the galactic science contributes specifically on particular regions of interest, the metrics depend on pre-computed science maps of the desired survey region of each science case. Now, you can choose which map you would like to calculate the metrics for, either the overall combined science map, which includes all of the science cases, or you can any one of the constituent maps for different science topics. So in this case, I'm going to use the combined map. So now we can go ahead and run the metrics, and we can calculate the metric for this science map using the framework provided by the MAF. This allows us to run multiple metrics at once, giving the MAF a list of metrics. Now,
sorry for interrupting. Could you increase the size just a little?
Oh,
Maybe
yeah.
too old.
Yeah, so
Oh,
is that better?
perfect. Thank you so much.
Okay, of course. Sorry about that. So here you can see a simple Python list, and I've declared the galactic plane footprints. You can also see the time domain, the time cadence metrics declared as well, and you can add those to the list and just simply calculate all of those metrics at once. I'm going to stick with just one metric right now because it takes a little bit of time to calculate more of them. So I'll just run that cell. Before we can run the metrics, though, the math does need a little bit more information. We can calculate the value of the metric over different spatial regions of the sky, called the data slicers. Almost all of the science metrics are calculated for the heel pixels, so I declare a heel pix slicer from one of the MAF's built-in functions. Next, we can tell it to select a subset of observations from the simulated survey using this constraint. Now, you can leave this string blank if you prefer, and that will calculate the metric using all of the observations in the whole simulation. In this case, I've chosen to add a constraint that will select only those observations which reach a given limiting magnitude. And that excludes some of the shorter exposures which are unsuitable for my science particularly. Okay. And the last constraint that we have is another optional constraint. This allows us to control the plotting ranges for the graphics that the metrics will automatically produce. And this is also optional, so you can leave that out if you prefer. And now we have everything we need to run the metrics. So we have the dangers of a live demo. I'm going to set this running and hope it works. There we go. So this cell completes the construction of the list of metrics, and it then uses the MAF framework's functions to repackage that information into a form where the metrics can be run. And then it calls the MAF's run all function, and that simply runs all of the metrics in the list that you gave it. The next cell in the notebook, that's going to take a little bit of time to compute. So I'll talk about the next cell in this notebook, which describes the actual output of this particular metric. The galactic plane footprint metric, excuse me, produces metric values of the number of observations matching the criteria for the given heel pixel within a desired survey footprint, and the number of observations multiplied by the priority of that heel pixel for a particular survey, particular science case. It also calculates the reduced metrics, and this means it calculates for each of the variability timescales of the different categories of variability. It selects those observations from the heel pixels which actually have a cadence adequate to detect variables in that category. And it outputs a plot of the surveyed heel pixels that actually receive that at least the minimum number of observations that would allow those objects to be detected. And so now you can see that that has finished calculating. And we can move on to the plot all function. And this will generate all of the automatic figures that the math is designed to produce for free. So that saves a lot of time in writing plotting code. I'll take a little look at, there we go. And you can see some of the plots that I just described, the number of observations per heel pixel in the sky. It also provides some plots of the areas surveyed as a function of the magnitude And this is produced for this indicates the number of observations as a function of the priority that the Heal pixel is given for different regions of the sky for galactic science. And you can see it outputs this for all of the different categories of observations. So there's a lot of output to review there, and it's very informative for galactic science. So the last point I wanted to mention is that it's often useful to access the actual data values from the metric, which are produced for each point on the sky. And you can do that through the bundled dictionary object that we generated earlier. If you list the keys from this object, you'll find that they refer to every permutation of the metric that we just calculated. So that is, in this case, for the footprint metric for the science map that we chose for each category of variability timescale. One word of warning about accessing the metrics, though, is at least accessing the data values, is that the metrics produce a value for every Heal pixel on the whole of the sky. But of course, Rubin is based in the southern hemisphere and it can't observe the whole sky. So the metrics fill in null values for regions of the sky that Rubin can't observe. And there have been seen some data artifacts that do come from some of the metrics for those null regions. So you have to be careful and make sure that when you extract the metric values from a HealPix maps, to fill in the null values with a 0 value. And that then gives you much more sensible metric output. And you can see here from it returns a simple Python array from which you can then calculate whatever analysis you intend to do with the output. Okay, so that's it. Running a math, the same procedure will happen for any other science metric that you would like to run. It would be very, very similar to this. And you can find a number of example notebooks for other science cases in the resources that I shared earlier. So I will conclude this demonstration now, and thank you very much for your attention. If you have any questions, I'm of course happy to answer them.
All right, thank you, Rachel. Any questions for Rachel? Martin? And then Bruno.
Yeah. Can you hear me? Hello.
Yes.
So when you get to the slicer and you want to choose the number of pixels, if you want to choose a very high resolution, does this increase a lot the computational time? Yes.
It's going to scale linearly with the number of Heal pixels in the sky, simply because you're repeating that calculation. So if you run that on a cluster computer, then it's not too bad. You saw how quick it was to calculate a single metric. Typically, it takes minutes. But yes, if you increase the resolution, that time will go up.
Bruno?
Yes, thank you. Very interesting talk. Thank you. So my question is actually related to all that you have talked in your slides, about the strategy. So you have the scheduler, and the scheduler would handle daily life of the observations, right? But is it expected for SST observing strategy to evolve during the life of the survey? What happens if a certain probe finds out that it needs more data, better data, or something like that? Is that possible?
It is possible, and perhaps at this point, Federica would be the ideal person to answer that question because she chairs the SCOC committee. My understanding is that the intention is to continue the evaluation of the survey once it starts. Effectively, we get a new OpSim database. It's just a real live database, and we can then apply all of the same metrics to the output. And we can evaluate whether, on an ongoing basis, whether or not the survey is actually delivering the data we need it to deliver for the different science that we want to do, and perhaps any new science that comes up. I mean, 10 years is a long time. There could be new discoveries made, there could be entire new branches that come out, and we may need to adapt accordingly. So yes, is the short answer. It's an ongoing process.
Can I ask? Yeah,
Sure,
excellent answer.
go ahead.
Yeah, just and then I guess I can extend this next question, which is linked regarding the commissioning stage. So do you envision during commissioning to find out new key information for your metrics, new key information for the scheduler, or whatever, that makes us change a little bit or our view on how the actual survey will be conducted?
Yeah, that's a great question. And I think the biggest thing that commissioning is going to answer is it will give us a very realistic idea of what the operational overheads are for the facility. At the moment, what we have is the predicted idea of how long it's going to take the camera to read out, the prediction for how long it's going to take to slew from one side of the sky to the other. What we don't have is actual on-sky data. And that is one of the many things that they're going to be testing and measuring during the commissioning phase. And that's going to give us a much more realistic idea of how long it takes us to get a given observation, and therefore how much time we have available on sky during that 10-year survey period. And obviously, once we have a better handle on how much time we have available on sky to survey, then we have a better idea of how we can distribute that time between the different science goals. So I think, yes, commissioning it's going to be a very important aspect of that.
Any other question?
Thank you.
Mariano.
Thank you. Thank you for the great talk, Rachel. I would like to ask you about, there is some of the proposals that looks like dedicated surveys. It will be more opportunities to suggest this kind of proposals. For example, for instance, thinking on the unknowns that Federica took, or I don't know, for instance, supernovae, gravitational lensed supernovae, and this kind of subjects could be opportunities to change the plan of observations for this kind of small projects.
So I think perhaps Federica is best placed to answer that one. I think LSST would not close off any exciting science that comes up. As we go towards operations, obviously we need to have something.
Sorry, I heard my name, but I didn't really understand the question.
So if I could, sorry, Fed, I'm getting some feedback here.
Hold on 1 second. Yes, I was. My audio from the headphones was disconnected.
Okay. So, Raphael, perhaps you should restate the question.
We can hear you, Mariano. Mariano, you are mute. No.
Sorry about that.
Don't worry.
Sorry.
No.
I was asking Federica about the possibility to make a specific request about like small surveys along the project. For instance, looking for nodes objects, like you suggest or doing analysis, for instance, of supernova with gravitational lensing effects and this kind of things. There will be a place to put some small proposals.
So I heard, but not too well. But I think I understand the question, which is, so I want to say that you really want to think about Rubin as a survey telescope. So you really want to think of it as having a set of surveys that are designed by the time the observatory start, and that's what the observatory focuses on, and particularly that the wide fast deep is the priority. So don't think about it as a place where you can have PI programs, right? Having said that, the SCOC is a standing committee in operation, the Survey Cadence Optimization Committee, which means it will continuously review the performance of the observing strategy, the performance of the observatory, and how they interplay, and whether or not the goals that we want to achieve are being achieved, as well as whether other scientific priorities arise that really require shifting the priorities of some of the observing, notwithstanding the fact that there is a commitment to the 4 science pillars. So don't think about it like I would like to propose that they give me a certain set of hours to spend it in a certain ways. Think more of how will the survey altogether evolve over the 10 years, because the scientific priorities will have evolved. With one small caveat, which is that there is potential to have a small amount of time to be dedicated as sort of directory discretionary time. That's not ruled out. But I would really primarily focus on thinking about, can I demonstrate that the scientific priorities have changed and therefore the mini survey landscape might want to change.
Thank you so much, Federica.
Thank you.
Of course.
I have a question myself. Perhaps it's very basic. So I don't remember the name, but there will be a small telescope before the big telescope taking images, right? I don't remember what was the name of this pre-commissioning camera or something like that.
Right? We call it AUXTEL or auxiliary telescope.
Yeah. So that will try to mimic any of the cadences of the survey, so we can see if the cadence works for a given science, or how is that gonna work during the time that it's gonna work. I mean, before the big telescope.
So my understanding is that AUXTEL has actually started its observing program with the CONCAM, the test camera. And at the moment, I understand that it's doing effectively some technical practice runs, as it were. And this tests the operational software of the telescope itself. So it demonstrates that the telescopes can slew and take an exposure. It demonstrates the data handling system. It demonstrates the pipeline, that kind of sort of real world practical test, rather than necessarily science observations. There will be science observations made during the commissioning period, although perhaps a better description of them would be targeted small surveys designed to focus on particular technical aspects and demonstrate particular functionalities, such as, how well does it observe in crowded fields, how long does it take to slew, that kind of thing. The data availability from some of those commissioning phases, I understand that the data will be made available on a best efforts basis. So there will be real world sky data made available, but the timescale for its availability is not, they're not making any promises. I mean, at the end of the day, telescopes in commissioning, and the AUXTEL is part of that commissioning process. So Fed, perhaps if I misspeak, you will jump in and correct me here.
No, I think everything was was along the lines of how I understand it. AUXTEL particularly is really designed to take images to demonstrate the technical scope, that the technical scope has been achieved. Images with COMCAM, the commissioning camera, will begin taking images in commissioning. And like Rachel said, the priority there too is to ensure that the survey has met the required standards. And there are also a bunch of teams from the community that have proposed and are participating to commissioning, which will have access to those data, but that too, the priority is for them to help commissioning and make sure that the survey hits the ground running on day one.
Okay, thank you. So any more questions for Rachel or Fayed? No? Then we thanks again, Rachel.
Thank you.
Thank you so much. So now I think that Martin is following as a chair. Okay, I can hear you, Mariano. No?
Okay.
No,
Great. I would like to suggest that we made a brief break, just 5-10 minutes, take a coffee. There's a lot of time to be online.
Sure.
Sure. And we will resume, I don't know, in 5 minutes.
Okay.
Fine.
Thank you, Fred.
5
thank
minutes.
you.
Okay.
Thank you, Federica. Bye. 5 minutes.
Thank you so much.
Okay, so we are ready to go back. Can you hear us now?
Yes, yes. Now I hear you.
Okay, so it's a great pleasure to introduce Emille Ishida. I won't go through the bio because that would be too large, but just say that she's originally from Brazil. After getting the PhD, she's been in several places, and now she's in Clermont-Auvergne University. She's been very involved in statistics, in astrophysics, and also in machine learning astrophysics. There's a book on Bayesian astrophysics, Bayesian methods in astrophysics that I just learned. It's been used in this university. So
Oh,
she's been one of the leads of the FINK broker. So we'll start learning about brokers. Thank you, Emily.
thank you. Thank you, Martin. Thank you for the invitation, and I'm really happy to be here. And I hope next time I can go in person if the world ever comes back to normal. But I'm super happy to talk to you today about the FINK broker. So let me share my screen. Moment. Can you see this screen? Can you see the screen? Yes. Okay.
Yes, we can see the screen.
Okay, good. Okay, good. So I'm going to talk to you today about the FINK broker. So first thing that I have to tell you is that I'm here talking about work of mostly is not mine, it's a very big group of people. FINK started 3 years ago and is mostly based on France, but we have important branches in the UK, some people in the US, and also Australia. So let's talk about this. I don't have to introduce to this crowd the idea of the transient sky. I think we are all aware that some interesting things happen in the sky that change with time, and that we would all like to use LSST to study those things. And then also, I'm very happy that I don't have to introduce to you for the Rubin Observatory, because it has been beautifully introduced before. The one thing that you have to remember is that this will generate around 10 million alerts per night. They are all publicly available. You can do anything you want with them, but this is huge. Like it's a lot. It's a lot of data. So the idea is to use the broker systems to try to mine that data somehow. So just a little bit more exclusive for the purpose of this talk, what do I mean about the data path? So you have the telescope, something happens on the sky, you have a difference image analysis. Every time there is a signal, something different from the template image, you generate an alert. An alert just tells you there is something in this point of the sky that is different from what it was before. And we expect to have 10 million of those per night. Those alerts are sent to brokers, which are systems who have the task of filtering the alerts and separating however they want. So they can filter, cut, machine learning, catalog association, cross-metric, all these streams or things like that. And the goal of the brokers is to separate an interesting subset of the stream and distribute that to the scientific community, which only want the interesting ones. And what is interesting depends on who is listening. So these are many different communities that want different things. So just for the purpose of this talk, so I can do this a little bit of jargon here, I'm always going to be talking about alerts. So what is exactly an alert? An alert is based on the difference image analysis. So it contains information about every time you compare the science image with the template image, and there is a signal there. It generates information about that detection in particular that was generated today, about some cross-match or some contextual information about that observation. And also it's going to include historical photometric history of that point in the sky, and a little image stamps. So this is an example of what you have here. You have the science image, you have the template image, and then you have the difference image. So these are small stamps where you can check what exactly is happening during this alert. And so since LSST is not functioning completely yet, we are now working with ZTF data, but the format of the alert would be more or less the same. For ZTF, this historical information of the object is 30 days. For LSST, that would be up to a year. But the overall way that we deal with the data is supposed to be very similar to what is currently happening with LSST. So in order to do this, to distribute this data stream coherently, the Rubin Observatory made some selection, I think a year ago or something like that, where groups from around the world applied to receive the entire unfiltered alert stream. So this was a competition, and 7 groups were selected for to receive the complete alert stream. So we probably heard about alerts in Chile. In Europe, we have FINK and Laser, and in the US, Babamu, Antares, and Google. So these are the teams that are going to receive the unfiltered alert stream. And then each broker has their own way of dealing with the data and separating what is interesting and what is not for their communities. So just a little bit of the technical part about how FINK is designed. The difference, FINK is probably, FINK is a very young, let's say, experiment. We started 2019, so we have like 3 years now. And the main characteristic of FINK, like it was developed specifically for LSST. So FINK didn't exist before. So it's not a system that was built for a previous survey. It was built directly to deal with the data challenges and the infrastructure that will be necessary to handle the LSST data volumes and complexity. So you have basically the mainstream that comes. Once the data arrives, we have a storage, but the user itself never interacts with the storage. So the data, the user is going to be interacting with the data through or the filters stream and the API or the science portal. So I'm going to talk a little bit about these two now. So how do you get the alerts? So now you know that you have the telescope, you have transients, and then you have alerts that are generated. So how do you get alerts? I put link here, and I am going to I'm going to leave the slides afterwards so you can play it for yourself. But I just wanted to explain a little bit what you can do, and I hope my internet collaborates today. So, for example, from the web portal, you can see many different. There's many functionalities that you can use from the web portal itself. So, for example, if you are interested on solar system objects, for example, if you click here on help, it will give you some examples of what you can search for. So if you come to the solar system object and, I don't know, choose a random one, let's see what happens here, and try to search for these, you can find a list of all alerts associated to that object from the Minor Planet catalog. You have a sky map, which is not going to work. Oh, it works. So you can see here you have the sky map, which is from Aladdin, that you can look at this. In the table, you can also, for example, make queries here if you want. I don't know, you have a given specific question that you want declination. You are not seeing, you are seeing the screen, right? Okay, sorry. Or you can do other types of search. For example, you can do con search or date search. These are all options that are there. If you go to the object ID, I separated one here that is nice. So I'm going to just so you can see. I was afraid that my internet would not work. So you can take the object ID if you know what object you are searching for and make. Yeah, this is what I was hoping it was happening. It's my internet. Okay, it's here. So you see that you have the object ID here, and once you click, you will have this web page that will show you all the properties of these objects specifically. Okay, I'm taking this one because my internet is low, but here you can see that you have an image of the of this location. You have all the alerts associated to that object, the 3 postage stamps, some other information about rates and distance if there is a cross match with Simba or the Minor Planet catalog or something like that. And here you see that you have many different tabs, and these are the modules that are already implemented in FINK. So for example, if you go to the supernova module, you can check how the probabilities of the supernova classifier evolve with time for each one of these points that you have. And also you can check cross matches of these particular objects with many different sources. So TNS, Simba, the NAD viewer, many different things that you can see. And also you can play with all of the other tabs that are there. So I'm just going to leave it here so you can play with this. You can get the object data also that it will, if you click on this object, get object data, it will give you the small code that you need in order to take this from a Jupyter note, from a notebook or the terminal, for example. And you can inspect the data for these for the last particular alert, the last alert associated to this object. So these are all of the columns that you have things associated with. Obviously, this is very nice and very good for visual inspection, but it's not super interesting if you want to actually take a lot of data out of it. So this is just a way for you. I just wanted to show how you can visually inspect the data if you have already an object that you have in mind. But obviously, normally, what we want to do is to query a lot of data which for filters that you define yourself. So for example, you have cuts on right ascension declination, you have cuts on dates or a specific time frame or things like that. So you have the API, which you can do that specifically from Jupyter Notebooks directly. I will leave all of these links are in the presentation, so I'm not going to go through you with all of this. But for example, if you want to explore the database, you can, and you have the equivalent of what I showed you in the visual inspection. You can do it with the object ID and get upon this data frame with all the information about that object that you want. Equivalent, you can make a concerted, so you define right ascension declination and a radius around which you want to do the search. It will return you all the alerts in that particular area. You can also do, for example, a query made on time. So you can define a date and a window of how many minutes or do you want to look for all the alerts that were received within that time frame. And we also have cross-match with different catalogs. There is a functionality that you can upload your own catalog and cross-match with your own catalog. But for example, if you want to have all the alerts associated with TNS, spectroscopically confirmed supernova, for example, you can do queries like this that would all this TNS supernova classified between this and this date, that alerts between that and that date. So these are just different ways that you can get information from the data. And also, one of the things that I told you is that the goal of the broker is to add value to the alerts, right? So the alerts come, and it is one of the goals to the broker to add value to this. Means what? Classifications based on whatever the broker wants to do. In this case, for example, FINK has an early supernova 1A classifier, which is based on machine learning models that I'm going to talk more about. You can make a query and say, give me the latest 200 alerts that were classified by the early supernova classification model. So these are all ways that you can get your data from the broker, and you can query the stream like that. But the point of all this is obviously that this is the science case dependent. So you should be interested in 1As in order to want to get this to make this type of query, for example. So the question that we have now is like, how do we classify the alerts, right? So I am going to give you an example of the early supernova 1A classifier by the simple meaning that I am a supernova person. I have a background in type 1A supernovae, but the same method applies to any other science case that you want to do. The mechanics is the same. It will just change the model that you are doing, but all of the infrastructure will be exactly the same. So again, you have these telescopes, you have different image, these produces alerts, goes to the brokers, and the brokers have to distribute this to the community. Okay, so this data stream that comes from here to here contain alerts. So I'm going to divide this in two different worlds. So this will be the broker world on top, and this will be the specialist world. This is you. So this is what we normally do when you are trying to find your sign. So you get the data, and you can get this data via the FINK API and build your training sample. For example, you can get all the alerts which has a spectroscopically confirmed classification on TNS or SIMBA, for example, to build your training sample, as an example, okay? So you can get this data, and you have all the alerts that you can use to do your machine learning model. So once you have that, this is what we normally do. You take your labels, you divide that between train and test data. You have a machine learning model that you are going to train using this data, and you're going to repeat this until you give up or your deadline arrives, whatever happens first. So you will do all this, and then once you are happy with your model and you finish training your model, what you're going to do is you will have a trained model plus everything that you need in order to classify new alerts once they come. So this will include feature selection if you have any, selection codes, auxiliary data if necessary in order to run your model. And this is the package that is going to be uploaded to the broker. So in this, you can not only use your own model, but you can use everything that is already in the broker and match that and make some connection with the model that you developed yourself. So FINK was specifically designed to be modular and to accommodate things for LSST. So normally I tell people that if you have, FINK is especially good if you have a very weird question. So if you only want like a simple cut or a filter or things like that, obviously we can do, but this is not the full capability of the broker. The broker, FINK was built to allow the user to make very weird questions. So once you have whatever model you have, for the broker system, it doesn't make any difference. So for us, it all will be the same. It will only be a function that inputs something and outputs the classification, and inside of that, you can do whatever you want. So in this case, for example, I will give you, as I said, the example of the early supernova 1A classifier. Okay. So what is the first problem? The first problem was something that Federica already said before, that we do not have labels, because labels in astronomy mean spectra, and that's very expensive, and you're not going to have labels for everything that you have photometry for. That's not going to happen. The second problem is that the training, given the nature of the spectroscopic data in comparison with the nature of photometric data, those two things are not representative of each other. And representativeness is one of the main hypotheses you begin with when you are building any machine learning model, right? So basically, in very simple terms, what you have is you have a data situation where the ideal data situation, you have a training sample with features and labels. So here you have light curves and classes, or pictures and classes. And you want to learn everything you can from this and apply to another data set where you only have the features, right? So you need to learn everything you can from your training sample and apply that to your test sample. The problem is that the real data situation in astronomy is like that, and this is not going to change. So the one thing that we can do is try to optimize classification results, and there are many different ways of doing this. One possibility, for example, is extract information from simulations. And then you can, since you can generate as many simulations as you want, you can use, for example, deep learning or Bayesian neural networks or something like that. So this is one of the modules that we have inside the broker. This is a Bayesian neural network. There is trained to classify between supernova and non-supernova objects. So this is one possibility. The other possibility is to optimize the constructions of the training samples. So the problem that we have today is that we normally use, the only thing that we can do is to use if you want to train with real data, is to use the labels that we currently have. The problem is the labels that we currently have were never meant to be a training sample. They were gathered because people were interested in them for other reasons. And then you go there and you take this sample and build your training because you don't have any other option. But this is not how you should construct a training sample. So the idea of this optimization is using active learning. And depending on who you ask, this is going to be called active learning or optimal experiment design, but it's exactly the same thing. So the idea, very quickly, the idea is you start with a labeled pool. So you start with a pool of a small data set that you have labels for. And this is really small, like 10 objects or something like that, because you don't want to bias. You really want to start from very small information. You start with a very small labeled training sample. You train your machine learning model, so you find the boundaries between your classes here, and this is going to be very bad because you only have 10 objects for training. You classify your entire target sample, and then once you have all of these classified, the algorithm will tell you what is the object for which you do not have labels, but it would be more informative to your model in case you have the labels. So for example, if you are working on binary classification, 1A, non-1A, the algorithm will choose for it, one possibility is to choose the object whose probability of being 1A is close to 50%. Because that means that that object sits exactly in the boundary of my classes, and my classifier has absolutely no idea what to do with it. So I'm going to identify that object, send that object to a person or a machine, in our case, someone who will take a spectra for us and give us back the label. And once the label is available, we put that in the training sample and do it again. So you interactively construct your training sample, and a human does not make the decision of each object is going to be included in your training sample or not. So this is just so you can have an idea of how these things work in practice and the order of magnitude of those things. So we took data sets from almost a year of alerts with ZTF right now, cross-match with TNS and Cumbres, so for which we have classification. 7% of them were supernova 1A, more or less. We initiate the training with only 10 alerts, 5 1As and 5 non-1As, and that's it. There is some very simple feature extraction. It's just a sigmoid fit in the light curve. We run this operation that I told you about for 300 loops. And after 300 loops, this is what you have. So here in these plots, in all of these plots, the x-axis is the number of times that I made this iteration, the number of loops that I ran, and in the y-axis you have efficiency, purity, and figure of merit is just, you can think of this as a multiplication of one efficiency over purity, with the fact that with a penalization for false positives, because in type 1A supernova, if you have a 1A that you classify as a non-1A, it's less bad because it's a lost opportunity, but nothing so bad is going to happen with it. But you have a non-1A that you classify as a 1A, this can be bad for your further study. So there is just some penalty for that. But the only thing that you have to remember is that these numbers don't mean anything alone. The only thing that you want them to be as close to 1 as possible. And you see that when you start your training, it's very bad. So your efficiency is very high because the efficiency is completeness, right? So how many of the supernova that are there you are classifying as supernovae? So when I look at this plot, what I see is that efficiency is super high, but purity is super low, which means that in the beginning, the classifier is telling you that everybody is a 1A. If everybody is a 1A, your efficiency will be 100%, but your purity will be very low because you have a high number of false positives. All right. But after you run this for many times, you see that after a while, you get a clear difference between making an informative decision, which is the blue line here, which is the active learning loop I was talking to you about. And the orange line shows you the results you have if instead of making an informative decision, you just randomly go to the target sample, take one object and put that on target. So you're not thinking about it. You just take a random object and put it in the training sample again. So this is just to give you an idea of how these things evolve with the evolution of these loops. This is what is going to happen more or less in the lower part of my previous slide. So this is what is going to happen in the expert domain. So this is you, right? Not us. But once these things are done, and in the end, maybe you are happy with whatever model you find here in the end, because it was trained in a very informative training sample. And then you have your trained model. And then you are going to take your trained model plus your feature extraction procedure, and this is going to be uploaded to the broker. So now the broker has the result of everything that was done in the domain specialist world, summarized in the trained model. And here, as I said, you can combine these things with other options. So you can cross-match this with catalogs. And in this case, we made cross-match with catalogs, so we don't, just to make sure that this object was not already classified by someone else, and agreement with supernova, because this is a early supernova 1A, and supernova is supernova non-supernova. So the early supernova is a subclass of whatever happens in the deep learning classifier. So all of those things are combined together inside the broker, and then you have the classification results. So we have been doing this for a while, and these results that between November 2020 and March 2022, we have been reporting to TNS all of the alerts whose probability of being a type 1A is higher than 50%. So all of the objects whose probability of being a 1A is higher than 50% is being sent to TNS. And then somebody randomly, or not randomly, but not controlled by us, classify those objects, right? So there was 4,600 candidates sent to TNS. From these 4,600 573 were classified, spectroscopically confirmed by other people, and 80% of them ended up being 1A, which is interesting because if you remember the purity values that I had, it's actually around 80%. So actually, it's basically what we would expect from this result. Obviously, you have to see this with a grain of salt because there is still a human component in there, right? So we send the candidates to TNS, but since we don't control the label taking part, the spectroscopically follow up, there is still a human who looks at the light curves and decides if a label is going to take or not. So this is not a complete sample. There's a lot of caveats there, but it's just like reassuring to know that at least things are coherent to what we expect. From the other contaminants, you see that all of the others were other types of supernovae, and with that one luminous blue variable that was there for some reason. But all of the other contaminants were other types of supernovae. So there is, once you have this, so now you have your model is uploaded to the broker, and the broker is sending out streams. And then you can have many different ways of how you can access this data. So I will not have time to go through the notebooks, but I leave the links here. We have tutorials about how you can get a solar system object, kilonova, supernova, whatever. So I will leave the link, but I will not have time to go through it. But it's there, and we are more than happy to answer questions if you try to run and something doesn't work, but normally it should. So just to just to go to the other part. This is what we are doing now. So this is what we are doing with ZTF, right? For LSST, what is happening? So for LSST, we are going to close the loop, and this is something that also was mentioned before, which is the target of operation manager, because when LSST is in operation, we want this whole process to be automatic. There should be no human in the loop. So we have all of this process that's going to upload your model to the broker. Now, instead of sending to the community only the substream of early supernova candidates, we are also going to send around a wish list. So you will have the option to choose a wish list of things that, if we had the classification for these objects, this would improve the classifier. And once objects of this wish list are classified, there should be a direct Kafka stream that sends the labels back to the broker, and this process is run again without anyone needing to put hands on it. This is the plan. So this is what and FINK was specifically developed to accommodate this type of active learning loop during LSST operations. So I will not have time. My time is running out. But I do want to tell you that the same idea of that we are using, that I told you before about the active learning for classification, can also be used for anomaly detection. We have, with the SNAD team, we have done examples in catalog data where the fact that at each iteration you ask the expert feedback. So you have a machine learning model that gives you, instead of classification now, it gives you anomalies. And then each time you ask for the expert, is this anomaly astrophysically interesting or not? This information is put back into the system, and this designs a machine learning algorithm for your definition of what is an interesting astrophysics anomaly. So it has been said before by Federica that LSST will be a discovery machine, and this is completely true. But we need to have, we are not going to find anything if we do not have specific tools designed to find things that we are trying to find, because it's too much data and we are not going to just stumble on interesting things that are there. But this is just a parenthesis, because I think this is an interesting way that we can use in the future, and it's also on the plan for future FINK applications. We have a anomaly detection model that is currently being developed, but it's not in production yet. So I told you before, I gave you an example of supernovae, right? But now I also have to give you an example of of kilonova, for example. Kilonova is a different problem because there are no labels. There's only one. So there are no way you are going to construct a training sample from real data. So what you have to do is to construct simulations and try to find things with simulations, with the caveat that these objects are super fast. They last for, I don't know, like a week or something. So you need to adapt your feature extraction procedure, your model. But it's exactly the same methodology that I told you before. Once you have a simulation, once you have a feature extraction procedure, a trained classifier, you upload that to the broker, is exactly the same procedure. So this is a simple random forest classifiers with a clever design of the parameter space. So you see that this is a simulation. Obviously, the blue things are kilonova, which are reasonably separated than other things in the parameter space. And here we started to experiment a little bit with that feedback from the community that I told you before. So what we had was, we have these light curves, we trained the model, as I told you before. Once the model is trained, it's uploaded to the broker. Now it's a different community, so the kilonova stream goes. It was a Slack bot, actually, that was constructed for the Grandma team, which is a network of professional and amateur astronomers. So these are people with telescopes that followed up our candidates. Obviously, there was no, they didn't found a kilonova, but there was very likely candidates, or at least very fast candidates. And it was a very interesting idea, a very interesting experiment of how the broker can be used to engage amateur astronomer community, a community as well. So I'll just leave their paper here, because it's really interesting what the amateur astronomers were able to contribute to the analysis of this candidate. And just another example of things that can be done, we have satellite tracks. So nowadays, there's a lot of talk about mega constellation things. This is not this. This paper was, this study was done trying to see satellite glints, which is satellites that produce a very fast, very fast variation in brightness due to solar to the solar light from the sun, and this appears in the difference image analysis as a transient. It generates an alert. So we see that on average, 12% of all single frame events, are like 140 per night nowadays, are due to these type of things of false alerts in the alert stream. But it's also something that for LSST we will have to be very to be conscious about. So I just wanted to give you an overview about everything that it's possible to do. And obviously, I think all the broker should be seen as a tool for your science case of need. As I said, FINK was designed to be as flexible as possible if you have a very weird question. But obviously, the system evolves as more people are joined to the community and other science cases are added. But we are more than happy to talk to you about other interests if you have any idea of weird things you would like to talk. So I will I will leave here some notes just in case you have other questions. You also have links where you can see statistics from the broker, how many alerts does DD process, and things like that. And I will be more than happy to take questions. Thank you.
Thank you. We have questions. Okay, we have a question from Juan.
Yes, thank you, Emily. Very nice talk. You want weird questions? I have a weird question. So Rachel already heard me to ask this question many times. For Rubin, if there is a novae in the galaxy, most of the times it will saturate. So that image, when it goes through the difference image, is going to be throughout. I think that somebody mentioned in the Link workshop a couple of weeks ago in New York that there might be a chance to have that saving somehow. Is there any way that the FINK will be able to issue an alert if one of the images is saturated suddenly?
I would say, so the brokers will always work with whatever comes out of the difference image analysis. So if I understand correctly what you're saying, maybe this would be one step before?
Yeah, it's say if the Rubin gives you that tonight we saw this star and then the last night it got saturated, that will go to some alert, I guess. And
I am not sure how the saturation will be dealt with. What I can tell you is if it generates an alert and this alert is sent, you will be able to get it. If the alert is produced and is included in the alert stream, yes, we can find it. But then I'm not sure how from projects this is from the different image analysis how this is going to be dealt with.
Yeah, and another problem will be to classify something based on saturations. But anyway.
Yeah.
Thank you.
More questions? Okay, I have a question. I mean, that's an amazing new word. It's amazing. Now, I think what the broker does is clear and its power. My question is more on what goes after the broker. So, okay, I can select. Well, if I have a telescope in my backyard in the beginning of the night, I would know now what I should do to get the events I'm interested in. I can make a query by magnitude, position, and type of event, and then I get a list, and I can decide what I would do. So my questions are twofold. One is how to automate this process. Is this where the toms go in? If I have a robotic telescope and I don't want to be awake all night, I just want the whole flow to be automated. This is where you have to plug a tom on the FINK broker, or what goes on?
So maybe Rachel is best to answer this question than I am, but the way I understand the tom, okay, Rachel is there. So Rachel, do you want to take the question?
I can do, but feel free to answer first.
Sorry?
Feel free to answer first, or I'm happy to answer as well.
Yeah. So I will tell what I know, which is not too much. I don't know too much about the toms, but there are spectroscopic facilities that are pre-registered or that are going to be able to deal with the tom, but this is not something for any spectroscopic facility. I think that's the question.
So if I may elaborate.
Yeah, sure, please.
That is certainly true. Some spectroscopic telescope facilities will remain human operated. That doesn't necessarily mean that you can't submit observation requests to them through a programmatic interface like a tom. Some of them will be accessible that way, but no doubt some telescopes will be doing their own spectroscopy in the traditional way. So what you have in the diagram in front of you is quite correct. The astronomers will be manually interacting with the telescopes just as we have for thousands of years, or at least hundreds of years rather. But also the TOMs will be there to automate some of that observing program wherever possible.
Thank you. I have a follow-up question on that, which I don't think it's in the realm of the brokers, but anyway, a lot of people would be interested in this kind of transients, let's say kilonovae, well, let's say supernovae, because there is a lot of them. And there's a whole network, let's say, of 2-meter telescopes around the globe. So how to avoid 100 people to be following the same 100 supernova, instead of each of them be following a different supernova and you get the 100 of them? Is there an answer to that?
Yes, I also think that's work for the TOMs.
That is something that TOMs can help to coordinate for sure. There are TOMs that have been programmed to talk to one another. So this is each individual project has an independent TOM system, but if they choose to share information, in order to coordinate their observations, then the TOM provides a way of doing that automatically. So that has been done already. There's also systems like the treasure map system that is in the process of being built and going on Sky. That's intended for coordinating observation programs in the follow-up of gravitational waves, for example, but it could easily be applied to other science topics. And the way that it works is that it acts as a database of observations that people plan to make or have made of a given target. And it invites observers to submit observations that they're making. And that then goes out on a public interface to the whole community so that people can coordinate that way.
One, just to complement that, one thing that we have been talking, for example, with the nowadays with because the TOM will work between, I have a candidate list that needs spectroscopic observation and how to get that spectra and distribute that resources, but there's also this dashed line, which is once that label is available, it has to come back and it has to go back to the broker in this process. All of this needs to be retrained. And if you think that LSST will run for 10 years, retraining this, it becomes more and more expensive as time goes by. So the model is better, but it's also more expensive to train. So what we have been talking, for example, is with systems like TNS, to have a Kafka stream that automatically would send to the broker once someone, for some reason, posted a spectroscopic classification to TNS, that we could have a Kafka stream to have read directly, so this process can be automated, which is another step of the pipeline.
Thanks, Emily. It's an impressive amount of work. Congratulations. Just to ask you two questions. One is we will have the opportunity to put our own training and machine learning methods. I understand. It will be possible to do some kind of data augmentation against the FINK features, for instance?
Yes. So in the process that happens in your world, from this red line to the bottom, you can do whatever you want. You can augment the data. You can do anything you want to train. The point is that once your model is trained, you need to have a clear, we need to be able to apply everything that is necessary to classify an incoming alert. So you would have to provide us with that recipe as well. So, so if you use the data augmentation only for the training process to give more information to your model, but when a new alert comes, you can take the alert and classify it directly, then the training model would be fine. But if you also need to do, sometimes you need to do like operations, quality cuts, and if you want to augment also the alerts that are coming for classification, then that recipe also needs to be uploaded. But it's not a big deal, like that can be done.
Right.
Well,
and another question is, there is the possibility to add information from another source different from LST. For instance, I'm thinking this subject that detected just once in LST, and you have an information from another catalog or telescope. And I don't know if it will be possible to go upstreams against LST data from FINK, or the system is designed with the flow that is shown in the in this slide.
Yes, so at this point, I didn't show it here, but at this point, you can, we cross-match with TNS and SIMBA, but there is also the possibility that you can upload you can cross-match the stream with your own catalog. So if you just format, if you have your private catalog, obviously there are limited size issues, but if you have your own catalog that you want to cross-match with the stream, that's possible already now. And we hope, this is under development, but we do hope to have cross matches between different the alert streams from different wavelengths. So, for example, we have been working with people from SVON, from the SVON mission. There for other people who are interested in GRBs or things like that. So there is the possibility to cross match the LSST alert stream with other alert streams from other, with, I don't know, gravitational waves or things like that. So that is a possibility. Yeah.
Oh, that's great. Since maybe there are a lot of people interested on complete the light curves, putting more data points between the observation from LST, and that could be useful to complete light curves and classify the topics. This is amazing, but really it's incredible. Thank you so much.
Yeah, you are talking about photometry, right? So you want to augment the data with photometry from other sources.
Yes, photometry, but also could be data from different multi-messengers like gravitational waves or another.
Yeah. So my question, we have a lot. We get that question a lot. The current answer, this might change in the future, but the current answer is multi-messenger, yes. Cross-matching with other streams for other wavelengths, or making that's fine. Combining photometry, at this point, we don't plan to do it, because combining photometry is very complicated because of calibration issues, and there is a whole bunch of other problems. So at this point, the answer is we can cross-match with other alert streams, but we're not going to do we're not going to mix photometry from different surveys. This might change in the future, but now this is the answer.
Okay, thank you so much.
Any more questions? Okay, if there are no more questions, let's thank again the speaker. Thank you.
Thank you.
One.
So our next speaker is Rodolfo Angeloni. Rodolfo, can you hear us?
Yes. Good afternoon, everyone. Buenas tardes a todos.
We can hear you clearly. So it's a pleasure to introduce Rodolfo Angeloni, a friend also. And Rodolfo was a former professor at the University of La Serena. Now, since last year, about, he's an assistant scientist at Gemini, and is currently the project scientist of SCORPIO, a new instrument at Gemini South. And Rodolfo is going to talk about SCORPIO now. Thank you, Rodolfo.
Thank you, Juan. I will just start sharing. And I think, please just confirm if you can see. Yeah, perfect. Okay, thank you very much, Juan, for the introduction. Thank you for the invitation. And again, my idea is just to present you this SCORPIO, the next generation instrument facility for the Gemini South telescope that is about to come. And I will try to put SCORPIO and its unique characteristic in the general framework of the observatory effort in be still at the forefront of this multi-messenger and time domain era. So I will give you a general overview of the GEMMA project, and then I will start slowly converging and focusing on SCORPIO and its characteristic, its general instrument design, and the science capabilities that have driven basically the design that I will describe just before. So a few years ago, as you probably know, the National Science Foundation awarded Gemini with a multi-million-dollar award to advance in the leadership of the observatory in this new upcoming era, plenty of nice and challenges. So the idea is to keep on track and make Gemini a symbiotic facility that can work and be harmonized with a facility coming online in the near future and the ones already active. The project specifically within GEMMA focuses on 3 main areas, and one of that, rapid response astronomy, I think is the one that mostly interested this audience. The general framework is that thanks to GEMMA, the Time Domain Astronomy project will develop the infrastructure for incorporating the telescopes, both Gemini North and Gemini South, of course, into the EON network. And this keeping in mind, considering the Gemini will be, and not only within NOIRLAB, but even, of course, within the EON, the largest aperture facility that will thus enable the studies of the faintest and highest priority targets. The idea is to offer the entire package, let's say, from, of course, the follow-up observations up to an automated data pipeline that will be able to deliver to the PI, to the science user, science quality reduced data virtually in real time. So historically, due to its Q observing mode, Gemini has always done a lot of TDA, a lot of time domain astronomers. And if we just look at the statistics from previous years, we know that target of opportunities, observations, both in standard and rapid flavors, make up about 25% of the time overall charge to band 1. Of course, at the moment, the general train of observations is, I would say, quite manual and can be, of course, improved also in preparation, for a very likely higher rate of TO triggers. So again, with the idea of keeping Gemini as the premier facility for doing target of opportunities follow-up, there are a lot of changes and implementations that are taking place at the software level, and also, as we will see shortly, at the level of which the same science operations are performed. Why Gemini will be particularly suitable for this kind of science? Well, as I've just said, it's an 8-meter telescope. They are both Gemini North and South 8-meter telescopes, so they will be the largest aperture follow-up machine. And having one telescope per hemisphere allow, of course, an all-sky coverage. And we already offer a quite varied suite of workhorse instruments that are already actively doing Q scheduling and TO observations. Those of you who are already familiar with Gemini, will have probably already used both GMOS, know about GEMS and Altair as AO systems, respectively in the south and the north, and are probably aware that GHOST, a high-resolution spectrograph, is just being commissioning, and then SCORPIO is underway. At the moment, Gemini already works within EON via a plugin for the Tom Toolkit, and is available it's currently in use, at least if I remember correctly, since 19A semesters. Has been mostly used, for example, for LIGO and supernova target of opportunities. And here I have just a very short video made by Brian Miller. We can summarize visually, since if one image is more than 1,000 words, one video is probably more than 1,000 images, the way this plugin interact with the TOM toolkit to trigger directly the observations to the observing tool. And again, those familiar with the standard OCS software today used at Gemini will recognize both the interface of the observing tool, and will also recognize on the other side that, for example, phases like the observing schedule preparations and the nominal phase 2 setting of programs is not the easiest thing, at the time of interacting. It presupposes that you know pretty well the instrument details and the instrument configurations. It's prone to errors, and that's why we also have these figures within Gemini as the NGO and internal supports like Conduct Scientist. So this is basically a way in which you can trigger an observation from the plugin of the TOM toolkit and get directly sent to the observing tool in such a way that the Gemini staff receive the trigger and can, in a matter of a few minutes, salute to the targets and get the observations in the case of the rapid TOs. Then one of the core program of this Gemma project is for sure the Gemini program platform. There will be the core of I will say, a new concept observatory control system. It will be easier to use, replacing at a single time both the PIT and DOT. It will be web-based, so you won't have to download every single software. You will have as a PI within the same program both Gemini North and Gemini South observations. And if you are a Gemini user now, you know that this is not currently possible. And of course, from an internal point of view, it will make everything much easier to maintain. If you are interested in getting the details of more details about the GPP, I invite you to have a look at this web page and look at this talk on YouTube by Brian Miller and Stephens. And if you are curious, you can explore yourself the prototype of the GPP that is currently available. You can go, let's see if it works. Okay, you can go to explore.gemini.edu, and you will basically find this interface. There are still several tabs under constructions, but you can log in. Well, you can just simply act as a guest user or log in with your ORCID account. And you will be presented with different tabs that can already give you a pretty nice idea of how the GPP will look like and how the both phase 1 and phase 2 for this new update will look like. So, for example, here just the general proposal details. So something that is actually reminds you of our PIT phase 1 now. So here you can put the title of your program. You can decide what kind of program you are submitting. If it's a large program, a fast turnaround, classical observing, or just Q. You can decide, of course, which partner. We can assign here 100% of Argentina. You can decide the category. So basically the different keywords that your science will be referring to. And here you can fine-tune other parameters, and here decide what kind of standard TO you would like to activate. And this is basically the equivalent of your phase 1, sorry. And here in the observation, you can find already kind of couple of mock targets. You can create your own target if you want to play. So for example, we want to add a target. I don't know, I can just, the first one that comes from my mind is a very bright stellar object that you won't observe at Gemini unless you want to do spectroscopy under band 4 conditions. But just to see, you click, automatically you get the target, you get the finding charts, you get a summary of the target properties. Here in the same panel, you can already fine-tune the observing conditions that you are aiming at in terms of, for example, photometric conditions, image quality, water vapor, elevation range. You probably don't want to get up to Air Mass 3, and the moon phase. So here you can already see a kind of not so hidden and important change with respect to the standard conditions that we use today. The idea is to link these parameters as much as we can to real physical or scientific numbers instead of, for example, percentile bins like Gemini uses today, IQ20, IQ50. Here you can decide, specific extinction value or image quality. And here, then you can, this is something that would be a great advantage for users. Here you can decide what kind of science you are aiming at, spectroscopy or imaging. Currently, just spectroscopy mode is activated. You might say, okay, I'm interested in having, a spectrum around H alpha. I would be happy with 1,000 resolution, more or less, aiming at 100 signal to noise. And well, let's say just long slit. And the system will automatically start to match all the possible configurations of instrument, of course, telescope, and specific instrument configurations that give you the access to this science goal through these technical specifications. So, as I told you, the target is very bright, so it's just giving me now the 2 seconds. This is what is interesting to look at, is basically the instrument continually interfaces with the ITC. Okay, so for example, here you are presented with 43 matching configuration if you want to include Gemini, GMOS, Gemini North, so something that you, for this target in particular, probably you don't want to go, but here you have already the suggestion, and this automatically go also to the this is our constraint configuration that now it doesn't appear anything here, but if I just go back, let me see. Okay, on this, for example, this is another target. When you go to in configuration, for whatever reason, now it doesn't come anything, but you are actually already presented with a specific step of each sequence, both acquisition and science, that will be automatically and self-consistently set for you. Of course, if you're an experienced user, you can decide to twiddle around with the exposure time for the on-slit image, for example. But again, the system is, giving you already the entire package with your minimum effort. And this, again, is to make the operations and the observing preparation easier and faster for the community. So we can already anticipate that the community testing is supposed to start already this year. So if you volunteer for participating and provide your feedback, you are very welcome to do so. You can already go to the webpage that I just mentioned and play around and see how it looks like to you. And the full operations is expected by 2024. So it's at the very end, is not so far from now. Within the JAMA project, as I was mentioning at the beginning, there is also this idea of being able to deliver PI already a science quality data product. And in this respect, there is a software development towards a scheduler that will be basically able to provide night plans almost basically in real time. So again, for those of you familiar with Gemini operation, the human figure of the Q coordinator will tend to, I wouldn't say disappear, but to just provide a general overview of the weekly plan, because the schedule will take into account all the varying parameters, for example, the climate conditions, and optimizing real time the program that's supposed to be fed to the telescope to be observed on the spot. And then there will be also completeness of the Dragons pipeline that you probably already use for at least GMOS and other instrument in imaging mode, and that will be expanded to the other instrument in the course of the next few years. Said so, as a very general overview of the Gemini science operations, by 2024, hopefully, we will have also SCORPIO, a spectrograph and camera for the observations of rapid phenomena in the infrared and the optical. So SCORPIO is, if the LSST is a discovery machine, SCORPIO is his cousin in being a machine for rapid follow-up of rapid and dim transients. General overview, it will be, well, it is actually the next generation facility class instrument from the Gemini, for the Gemini South Telescope. And this essential is an imaging spectrograph that is able to deliver over the optical and the infrared range simultaneous 8-band imaging over a 3 arc-minute field with a pixel scale of 0.18 arc-second per pixel. Will be able to do very wideband spectroscopy of about 4,000 resolution with a 0.5 slit, 0.5 arc-second slit. And it will also be able to do high time resolution astrophysics, being able to take images with indefinitely long sequence with exposure time as fast as 50 milliseconds. And I was mentioning before, the commissioning is foreseen during mid-2024. So for its general concept, SCORPIO is designed, is envisioned as the instrument for the prompt follow-up observations of all TDA events that will be discovered not only by the LSST, but also by the other current large-scale surveys. This is the team, both the contractors team and the internal team Gemini. The PI is Massimo Roberto from the Science Telescope Science Institute. Project scientist is Alexander Barnett-Holst from the George Washington University. And one of the main contractors is the Southwest Research Institute, whose project manager for the SCORPIO project is Pete Roming. And here you also see the quite long list of subcontractors, where again the main one are these 4 that I just mentioned: Southwest, well, Fractal for the optics, John Hopkins, and the George Washington University. A very schematic view to make the instrument appear as simple as possible is this one. You basically have the light from the telescope entering from this side, from the left. It may or may not, depends on the user, pass through an ADC and enters into the cryogenic module where the infrared channels are hosted. You have a cascade of beam splitters, and then you have also at the room temperature the 4 optical channels. So again, simultaneously at the same time with just one single shot, you will get 8 images going from the G band to the K band. This is a 3D layout that hopefully will allow to understand better how the optical path is. Again, here is the light coming from the telescope. Here we have a first cryogenic window. Here is the focal plane where all the slit masks will be positioned. And here we encounter the first beam splitter that basically make the very first rough cut hard cut between visible and infrared photons. The infrared will continue within the cryostat, of course, and will encounter the different beam splitters that will make up the YJ and HK band. And the visible will be deviated towards a second cryogenic windows, an exiting window, then will impact on the visible science pole that basically will deflect parallelly into the main bench, the optical photons that will in turn be subsequently split in the 4 optical channels. This is an optical layout of just the visible channel. The infrared one is per concept is pretty similar. So you can appreciate here that the collimator, the visible collimator, is actually made by 2 main components. Here we have the main one. We have a first beam splitter, and then you see that actually there are second components for the collimators that are specifically optimized for the GR and the IZ band specifically. Then there would be another set of beam splitters. It's really a cascade until you end up basically with the pupil and the camera of the specific 4 optical channels, Z, I, R, and G for the optical module, for the visible module. Here is a CAD rendering of the visible optical bench, where again you see this is the full mirror. Then the light goes through here, encounters the different beam splitters, and get basically again divided into these 4 beams that will go and their path to the detector, on the detector of the G, R, I, and Z. Similar path will go for the infrared photons, but this time, of course, within the infrared band. There are no major moving parts, and this is something that's extremely important because you want to keep the instrument as stable as possible. And for those of you who are experienced with GMOS observations, the good news is that you will have in Scorpio the opportunity of deciding whether you want or not to use an atmospheric dispersion corrector. And here you can see the spot diagrams without and with the atmospheric, the ADC, in for different zenith distances and for different field positions. And you can actually see that over this circle that is 1 arc second in diameter, the ADC is behaving very well, because you even in the G band, the full width at maximum of your PSF will be, if I remember correctly, a number like 0.27 arc second, so well within the system requirement that was set to 0.34 for the G band. This is a 3D rendering of the focal plane mechanism that is basically the only moving part of the instrument, where you have different masks. You have a pinhole aperture, pinhole mask for calibration purposes. You have here the slit plan with the different slits, basically the same one that you can see here, with different aperture and different width. We'll show you later on the details and the nominal resolution. You have a spectroscopy mask that makes sure that only the slit center placed at the center of this mask is actually the one through that the light goes through. Then you have the full frame aperture mask that basically will allow imaging in the full frame mode, 3 by 3 arc minutes. And then you have the window mask that is specifically used for the high resolution imaging, and will have basically 180 per 18 arc second dimension. Something that will be important for what I will say in a while is also the presence of the slit viewing camera that here appears basically between the cryostat enclosure and the ADC unit. So basically here you have the light comes here that gets deviated by the slit that is reflected. There's with a reflecting material, and goes into the CCD camera. And this allows you basically to already during the acquisition to get the image of the field on the slit at the same time. This is the general throughput of the instrument without considering, without including yet the Gemini, the telescope itself. And you will see that the good, the advantages of having the ADC will result in a 10-15% say degradation of the throughput, something that you have to pay if you want to use it. And here are the performance in terms of image quality when using imaging mode. See that it's perfectly thought to match the best thing limited conditions that we currently have at Cerro Pachón. And here is just a feeling of what the limiting magnitude will be in imaging, assuming an average sync and air mass conditions and 3 days from the new moon, respectively, with and without the ADC, for 10 and 1800 seconds for reaching a synchronous noise of 10. So these are just numbers that you can keep as a general reference if you're already, thinking on how you could use Scorpio for your science. About spectroscopy, as I was saying, the resolution is roughly 4000 for the 0.5 arc second slit. You can go higher, and of course, we also have a very large slit width for calibration, for spectrophotometric calibration. And here again are the typical values that we expect under normal conditions for spectroscopy. So we will be offering 3 basic imaging mode, observing mode. There will be the imaging, where again, in just one single shot, you will get 8 channels over the entire 3 arc minute field. And the readout time are very short, just a bunch of seconds. You can actually, considering the limit imposed by the mechanical shutter, you can go down till like 1 second of overall exposure. The CCD will be able to read faster, but then you are still limited by the duty cycle of the shutter. You will have spectroscopy over the entire width of the detector, with the resolution that we just mentioned before. And then you also have this high cadence imaging mode that will be able to do high time resolution spectroscopy, where basically you are using this for direct imaging, just this small portion of the detector, and then you will be basically shifting the charge in this unexposed area of the detector. And this will allow high temporal resolution for very rapid phenomena. Scorpio has been specifically designed and thought since the beginning to be a follow-up, target of opportunity follow-up machine. So everything is designed to be performed as fast as possible. And again, for those of you who are familiar with Gemini observing mode and overheads, you know that already having a slit viewing camera is a tremendous advantage at the time of speeding up your acquisition time. With GMOS, for example, now you are still forced to take an image of the field in normal imaging mode, and then spend at least 2 or 3 minutes to configure the instrument into the spectroscopic mode. With a slit viewing camera, you basically are able to see the field and the slit position already since the beginning, and this is already a major improvement in the operations. And then again, we have this fast to readout mode if you really want to be fast and record as many images as you can for a sequence that with a 50 millisecond exposure can be as long as you want. Within the team and for the internal use, we are also developing this OMT, the Observing Monitoring Tool, because of course, still there would be an important part of human presence, you know, and the operation flow. So we wanted some software that when the night observer is sitting at the telescope will be able to handle, display, and do a very fast, on the fly data quality assessment in order to decide what next. In this sense, this observing monitoring tool will be able to process, display, and analyze the raw SCORPIO data that will be, you know, coming in with a very high rate in basically in virtual real time. And this won't be a tool, is not intended a tool that somehow overlap with the data reduction pipeline, but is a tool that is supposed to be extremely fast in such a way that right 1 second or maximum 2 seconds after we have taken an image, the night observer is already able to see the 8th channel on the display, have a first assessment about the signal to noise, even a rough photometry of the field that's been imaged. And this again to drive the next step, if to, for example, switch to another target or insist on the target to go for any kind of spectroscopic follow-up of deeper imaging that one might need. You can easily understand with that being such a versatile instrument, SCORPIO will hopefully and very likely deliver important scientific outputs over a very wide range of science topics. Of course, new transient, gravitational wave, here is just a list of interest from the SCORPIO science team, where each of us was thinking, you know, how to use SCORPIO for his own science. So you can find a bit of everything: supernova, X-ray binaries, AGN, interacting binaries. That is, for example, my main area of interest: exosolar planets, small solar system bodies. And we don't have a proper simulation yet, of course, but you can just imagine a rapid TO of a gravitational wave source, an alert coming in, and basically now the main overhead will be the slewing time of the telescope, just a bunch of minutes, and you will be able to immediately obtain a broadband photometry over 8 channels, broadband spectroscopy in this specific case, high time resolution, and you can on the spot decide what kind of acquisition strategy you will go for, depending also on the brightness of the target, what kind of near-infrared observing strategy you will implement. That can be the leader or the classical ABBA nodding. And so again, this is just, you know, if you have another kind of target where you are more interested for flickering, for example, and you would just want to go for photometry, you just switch to the high frame rate mode, and you will get up to 50 millisecond images for how many hours you wish. But again, being an instrument so versatile, actually probably the most interesting input will come from you, will come from the ideas that the user community will develop before, already at this stage, and when the instrument will be offered. So again, an invitation that whatever kind of science you are most interested in, already start thinking of how to use SCORPIO, because these inputs that we can get from the community are essential, and would probably, you know, also drive some decisions on how to offer the instrument when we'll have to make specific choices. And if you're interested, I can tell you after, during the question sessions, what I'm referring to. And then, like all the other existing and upcoming instruments of Gemini, also SCORPIO will be fully supported in Dragons. the Scorpio team, the Scorpio data reduction people is actually actively working on the pipeline already to implement the Scorpio data format within the pipeline, keeping the both imaging and log slick primitives, the ones that already exist, to reuse them as much as we can. And the idea is also hopefully to offer the nighttime quick look reduction tool for the target of opportunity observation. So something that would be really able, probably not as fast as the OMT that serves other purposes, but really fast in a matter of minutes, science quality data to the PI. So as I was saying, the instrument is now into the assembly integration and verification phase, and if everything goes well, as we hope, and as we believe, its commissioning phase is expected to occur at Cerro-Pasón around mid-2024. So I can just say, stay tuned, because nice year is coming, and thank you for your attention.
Thank you. Do we have questions? One?
Yes. Thank you, Rodolfo. I have two questions. Is there going to be any chance to propose objects for the commissioning phase?
This is something that hasn't been discussed. My non-official answer, but based on feeling, is that for the very beginning, I don't think so. Probably there will be the internal team and the building team that will basically have to. I would probably propose some target for the commissioning phase. Different thing will be for the science verification phase. There might be a first step in which there is this shared risk offer, and this is something that we might take into account. It's not decided yet, but we may, of course, take this option into account.
Another question is Scorpio gonna be mounted all the time in the telescope? So if there is a TOO, it can react rapidly, or if it is not mounted, you're gonna miss that TOO that you want to observe. How do you?
I think this is something that at an official level hasn't been discussed yet, because it will mostly depend also on the other existing and upcoming instruments, how they behave, what will be also the user request, because that will be also on a semester basis to see how much time is gonna be asked for Scorpio, how much time, for example, is gonna be asked for GSOI or iGrains2. So I think this is something that I cannot give you a definite answer yet. But of course, this also depends much on you. It will be so versatile that we hope that Scorpio will stay at the telescope for an important fraction of the semester, absorbing an important fraction not only of standard TO but also of let's say regular science of Gemini users, of the Gemini community.
All right, thank you.
Questions? So I have a question. So there are these three modes: the imaging, spectroscopy, and the fast one, right? Something that we can choose when we are going to observe, for example, is that if there is like TEO and we want to decide based on the magnitude of the object which mode to use.
Yeah, of course. There is also this general possibility in which, for example, many of these unexpected and TDA events, or I don't know, fast radio burst, we might not have any idea of what the optical magnitude will be. So an optimal and elastic, strategy will be just to go straight with imaging, and then depending on the magnitude on the fly, decide whether you want to go also for spectroscopy, or maybe just go deeper with imaging. That's why it's important to have a tool that is able to provide, good quality data or already science validated data in order to make a decision on the spot. So all the eavesdropping facility, for example, that we offer now at Gemini. So if one PI wants to assist, remotely from the observation, would be also extremely important in this case, because along with the PI, we can decide on the spot what kind of strategy. If it's just an automatic TO, then it's something that will be probably, described by the notes about the program. But yeah, in theory, you can decide, depending on your target, optimize on the fly the kind of observing mode that you're aiming at. And one doesn't exclude the other. You can start with imaging, and then you can pass through to spectroscopy.
There are more questions? Okay, if not, let's thank again the speaker.
Thank you.
Now our next and last speaker is Bruno Sanchez from Duke University. Bruno got his PhD in this very observatory here, and he's now very active in the dark energy science collaboration, working with supernova and other fields. So thank you, Bruno.
Thank you for inviting me. Yeah, thank you. So I'm going to be sharing my slides now. Let me see if this works. All right.
Yeah, it works.
Works. Okay. Oops. Okay. Let's present now. Okay. So I know it's very late and it's Friday, so I'm gonna try to be brief and then just talk a little bit about everything. It's gonna be a mix. Basically, I'm gonna talk about time domain science, specifically cosmology with LSST. So I'm, as Martin said, I'm a member of DESC, and I work in the time domain worker group inside the Dark Energy Science collaboration. And so, going straight to the LSST project, I know there's a lot of info that we got from Rachel Street already, from Federica's talk, also from what the alert brokers and all the alert related science Emille was talking about. So, but let me just recap very briefly. So the Legacy Survey of Space and Time is the Vera Rubin Observatory next survey. It's going to be conducted in the next few years, for 10 years. There are 4 science pillars in this survey. The first one is constraining the dark sector. There's also a lot of energy into making an inventory of the solar system objects in our vicinity. Also mapping the Milky Way baryonic matter, all the stars and gas in our own galaxy, and finally exploring the transient optical sky. So this means that this instrument is going to be doing a wide range of science. It's going to be a great advance for astronomy in many fronts. Here I'm showing you basically a schematic about the LSST camera in blue and in light blue, and then imposed over that you can see the DCAM footprint and then the Zwicky transient factory footprint on top of it. So considering that LSST is going to be as deep or deeper than DCAM, this is why LSST is going to change so much for us, the perspective on the transient sky and variability and all. So some key numbers of the observatory, we know it's a 8.4 meter telescope, effectively 6.7 aperture. What's amazing about it is that it has a field of view of almost 10 square degree. And then the pixel size is 0.2 arc seconds a pixel. So it has a very large field of view with a great resolution. And following what Rachel showed, there's multiple observing strategies. So we know that we're going to get a lot of alerts, as Emille was talking about with the brokers. So millions of alerts per night. Depending on the bandpass, we're going to get 30 seconds observations composed of 2 snaps. And we expect a median depth, 5 sigma, for point sources per visit of R, 24.5. So here on the right, I'm showing you the band passes. So we have 6 band passes for LSST, UGRI, ZY. So there's a lot of new exciting discoveries expected for this survey. Just to touch base again on the observing strategy, I'm just going to mention it. So there are several observation fields and observation strategies that need to be put together. There's going to be some compromise on different science fronts, but mostly the most important ones are the wide fast deep survey, or WFD, which is a very wide region that's going to be observed repeatedly. Then there's a deep drilling fields, which are dedicated small fields in which we're going to have higher cadence of observations, roughly by the end of the survey. In all bandpasses, thousands of visits in those fields. And then there's some compromise on what fields are going to be more, dedicated more time of the observatory time. Also, there's some multiple strategies that as Rachel showed, but there's rolling cadences and uniform sampling. So there's a compromise between these 2 different ways of observing. Here in the map, I'm showing what's the number of visits in kind of a color scheme. You can see that the ecliptic is being covered, and now also the galactic plane. And of course, this is all southern hemisphere. So with all the data that SST is going to be processing, the acquisition and the processing of this, it's going to be done at a higher rate than ever before. So the data acquisition rate in terabytes per night of LSST is expected to be 10 times the one that we saw in DES, and it actually will surpass the data volume of the precursor surveys only in its first year of operations. So this is a lot of data. It's a lot of processing, and the data management and the LSST project will only produce the acquisition and reduction of the data, initial production, but not going to perform or conduct the actual science analysis. This will be done by the science collaborations. So I'm showing you here a few logos of the science collaborations that are associated with LSST. The first one is the Transient Variable Star Science Collaboration, TVS. There's also the Milky Way collaboration. Here you have the Galaxy Science Collaboration, the collaboration dedicated to AGN. We have the Dark Energy Science Collaboration, or DESC. Also the Solar System Science Collaboration and the Strong Lensing Science Collaboration. And finally, the Information and Statistics Science Collaboration. So the data, as I said, is going to be served by the project for the community to do science. And the science collaborations are preparing to do very accurate measurements of different parameters of the universe and our universe using this data. So for Dark Energy Science Collaboration, I'm going to talk a little bit about what's the main goal here. The main goal is to measure the dark energy equation of state, and also to determine if it has some certain evolution in the history of the universe. So here I'm showing you the plots of what has been forecast for W, this parameter, and then WA, which is a component of the variable component. Basically, this is year 1 figure of merit, or what we call the error measurements on the determination of delta WA and delta W0 from a reference cosmology, and then the year 10 prediction or forecasting for these contours. So here I'm showing you all the combination of probes that DESC is going to use to measure this value, this parameter, very important parameter. It's going to be using supernovae, of course, weak lensing maps, strong lensing sources and clusters. It's going to measure clustering in galaxies, so basically measuring the large-scale structure of the universe using combined probes, the baryonic acoustic oscillations, and also working on this in a tomographic way using photometric redshifts. So you can see here how the contours are going to change through the years. And this is basically the ultimate goal of DESC. But how do we actually do this? So the task that DESC has to do is to develop and execute a higher level plan for the study of this dark energy with the LSST data. So basically, in simple terms, what we are doing inside DESC is to develop scientific pipelines that are going to be ready whenever LSST data arrives. So on the right, I'm showing you an image that shows the DC2 simulation. So the way DESC is doing this is through data challenges. So it's basically simulating the sky, simulating the observations that LSST is going to take, it's going to deliver, and produce a pipeline. So this is software to measure important parameters in those images. And so the main idea is to go end to end from the pixels all the way to cosmology. So here I'm showing you a single image and then a co-added image with all the sources that appear in these DC2 simulations. So the simulation, however, is just a small portion of LSST. It's only 300, relatively small, 300 square degrees, 5-year simulation of the observations of LSST. So basically, DESC has all the catalogs for truth objects that are being injected, all the observation parameters, and the simulated images would go from the raw images, just as they would come from the detectors. Then the calibration exposures, like flat fields and dark current, and then it will produce, using the LSST stack pipelines, all the processed visits or CALEX. On top of that, it has performed measurements like photometry and shape measurements and obtain color information and all the sources using the LSST stack. So, and here I'm showing you the 300 square degree area. You can see here, it's all tiled by something called tracts. Tracts are basically a small subdivision in the sky that the LSST will use to index the observations. And in here, I'm showing you only one of the tracks and only one of the patches, which is a subdivision of this, showing the co-added image, the multi-year, multicolor co-added image from these simulations. So inside DESC, we host a time domain working group. So the current leads of this working group, or co-conveners as we call them, are Mark Sullivan and myself, Bruno Sanchez. So, and in this time domain working group, we have a diverse and inclusive range of scientists, researchers, and developers with a lot of technical expertise coming together. So roughly 210 members participate inside this time domain working group. And it has been assembled from the previous supernovae working group and strong lensing working group. And now it hosts 51 projects, which are scientific projects with DC2 and with other data sets too. And it also has 4 topical teams. The time domain working group is also actively engaging in the future LSST commissioning stage, as the many other working groups inside DESC. So a lot of activity is going to happen in the next few years whenever we get the first images from LSST inside this working group. The time domain topical teams are the difference image analysis topical team, led by Michael Bubasi and Benjamin Rosin. The alerts topical team led by Rob Knopp and Alex Kim. They are also working on the broker, for instance, implementation for DESC, looking at the alert packages and how DESC is going to use them. We also have the strong lensing topical team led by Yashar Hezebe and Simon Birer. Basically, the strong lensing topical team is going to be working to find strongly lensed supernovae and all variables that appear in a near strong lens, and producing catalogs and of strong lenses and strongly lensed sources, and also algorithms to identify this. Finally, there's another topical team called the Supernovae Machine Learning Topical Team, led by Chad Schaffer and James Dumaine. And in this team, basically, the work is related to the classifiers and many other implementations, machine learning implementations that we need for our supernovae cosmology analysis inside DESC. The goal with the LSST data of DESC is to produce high accuracy measurements of the fundamental cosmological parameters. So if we consider just that, like globally, we also proactively consider synergies beyond DESC. For instance, to work with transient and variable stars, science collaboration, we know that there's a lot of work in common regarding supernovae physics and gravitational wave or kilonovae physics and so many other transients. Also, we work closely with the strong lensing science collaboration in developing what it will be the first large open source pipeline of strong lens detection and measurement, specifically designed for LSST. Also, we have synergies and ties with the IGN science collaboration. There's a very significant overlap in membership in all these collaborations within DESC, and this is central to us since many of the technical challenges that we will face are going to be rather common for all of us, like classification or photometrical calibration, and many other critical ones. I don't know if you have any questions at this point. Okay. Yeah, I can't see you, but okay. So, what have we done with within the time domain working group with DC2 so far? So, DC2 contains type 1a supernovae. So the observations that are in DC2, there's a large field of Wi-Fi steep cadence survey, and then there's a DDF portion. So in the Wi-Fi steep, we have analyzed the images, the supernovae type 1a images. They occur in natural density in Wi-Fi steep. So this is how they have been injected, including the angular and redshift and time densities. In DDF, on the contrary, we have an overdensity. And we also have both scenarios. We have hosted supernovae and hostless supernovae, and this is an artificial effect designed in the DC2 simulations, specifically to test our ability to detect transients inside galaxies or hosted by galaxies, and contrast that with the ones that are not hosted in galaxies. So the task that Time Domain Working Group took over is to develop the pipeline to find them, to find the transients in our simulation. So here I'm just linking two images. You can see how the background changes, hopefully, and there are two bright spots, let's say, that appear in one of the images. So the main technique to find that is to difference image analysis, which is to subtract a template or a deep coat image from just freshly taken image. So in this case, what we have done is to analyze a subset of 15 square degree of this field spanning 6 tracks, these subdivisions of the sky, this tiling structure that DC2 has and LSST will have, and processed all the pixels from the very raw state until we find the supernovae type 1a. So I'm showing you here in more detail and very schematically the 6 tracks that we analyzed. Each track is divided into patches, which are the individual portions of the sky in which we co-add images and take subtractions. And in gray I included all the supernovae that have been lost, and in red the ones that we found. So this small, quotation marks, small data set of 15 square degree comprises almost 2,000 visits of the LSST cam, or if we put it into CCD images, individual images, is almost 106,000. The redshift of the supernovae are from 0 to 1, and in this data set we have almost 6,000 of them. So here I'm showing some of the parameters of the supernovae, the type 1a supernovae that we have in this data set, showing distributions of redshift and the supernovae peak brightness or magnitude, but also the color and stretch parameters from the SOL2 model for the light curve. Here I'm showing you the rate model, as I said, observed natural density, then intrinsic scatter and many other parameters, not very important right now, but also in the very bottom panel, I'm showing what is the peak MJD of these supernovae. So, and I'm showing here a distribution of the observation times of our images. So you can see there's only 4 seasons here. So the analysis that we conducted used the first seasons to create templates or deep coads, and then we subtracted the remaining 4 seasons to discover transients. And since the light curves of the type 1a supernovae are not symmetric with respect to the peak MJD and the peak magnitude time, you can see that the peak MJDs that fall inside the year 2 are these subsets, and then it decays the number of supernovae we find, and then it rises again. Okay, so this is the schematic of the pipeline that we used. This is DESC difference image analysis pipeline. The whole point of this exercise is to test this piece of software. This piece of software, it's in charge of creating templates, running the subtractions, all using the LSST stack, intrinsic functions, the intrinsic routines. It detects sources, producing candidates, what we call DIA sources. I'm going to talk about that later. And it runs association of this into DIA objects, which are one or multiple DIA sources spatially associated. And on top of these DIA objects, it runs force photometry. So basically, it associates and runs photometry, obtaining light curves. And finally, we run a cosmology analysis, uses standard tools like the supernovae analysis package, and we obtain something like it will be the cosmology measurement in a future LSST supernovae sample. So, speaking strictly of the results in the subtraction images, we could measure what is called the efficiency. How we do this? So I'm showing 3 panels on the right. The top one has an image, which is freshly taken, a nightly image, let's say. And then in the middle panel, I'm showing a deep coad or a reference or a template, which is multiple images from the very first season of observations being coadded. So we compare them directly by running this DIA, the image subtraction routine, and we detect transients. So the detections...
Francisco. Oh.
Sorry?
Ma io penso che Sfera, sembra che sta più a 2 venire, perché c'ho, al di là delle scagarciate che o meno vari, c'ho soprattutto la notte e la mattina, non lo so, perché certe fitte proprio sulla parte, a livello del stomaco sopra verso la destra, cioè stomaco non destino.
Sorry,
cioè,
Rodolfo, we are hearing you, but I don't think you are talking to us.
A parte me ne pure riflusso, io non ho mai sofferto di riflusso. Mai.
Hello?
Mi vengono su certi cosi
I'll
di
try to mute him. I don't know if
io spero non sia che urcera, che pugnetta è stato.
It's fine. Did it work?
Okay, you can go ahead. Sorry.
Great. So, yeah. So I was saying that the idea here is to subtract the deep quad from the recently taken image, and then detect transients. The detections are basically pixels that are brighter than the background, that would should be the background, and these are marked in red in this plot that I'm showing you, in this figure that I'm showing you. And on top of those, I'm also showing the supernovae present in this image, and they are labeled with the signal-to-noise ratio of that particular epoch in that image. So you can see that some of them have a red candidate associated with them. It means they were detected. So this is why they're white. And then the yellow ones have no red detection. So basically they are the supernovae that we have not detected or missed in our subtraction. Also, there are candidates which don't have a truth a truth catalog object, which means that they are false positives. So if we repeat this with the many thousands images that we have, we can construct this plot on the left, which is the efficiency for detection of transients. So this is basically for every billion of signal-to-noise ratio, how many of the transients we were able to detect. And the single number that we use, or figure of merit, is the signal-to-noise ratio 1/2, which means at which value of signal-to-noise ratio we have the 50% chance of detecting transients. This value is 5.8 for the LSST stack across all band passes. The remark is that a lower signal-to-noise ratio 1/2 is actually better, but this value is actually comparable to DES results. So we know for a fact that we are very close in performance to precursor surveys, and with a lot of room to improve. Here I'm showing you the same determination, but in magnitude space. And since the band passes are different in this space, they are split into band passes. We cannot compare the magnitude depth of each band pass. So you can see again that the efficiency is high when the object is very bright, and then it drops. And we measure again the 50% efficiency cut in the magnitude space, and this is what we get for the different band passes. So again, this is very comparable to precursor surveys, and this is one of the many things that can be done with DC2. Pushing a little bit further, within DESC, what we have done is to use the light curves that we got from this type 1A supernovae. And there are multiple measurements of performance that we run on photometry, for instance, and photometry uncertainties and multiple parameters to test the pipelines. But the final figure for us was this Hubble diagram of standardized supernovae light curves. As a function of redshift, we create this what is called the distance modulus versus redshift diagram. And we also produce a cosmology fitting using a bias-corrected Hubble diagram, applying the standard correction formalism in the literature, using Monte Carlo simulations to predict what's the population of the light curves that we're going to observe. Contrasting that with the data, what we could find is that the cosmology that we can determine is within the uncertainties, is the statistical uncertainties of the true cosmology of DC2. So in this whole exercise, we went from the very raw images from the pixels all the way to W and omega matter, using this sample of supernovae observed in only 15 square degrees. So this is one of the many things that DC2 is doing for us in DESC. And another thing that is doing, and this is for the whole community, is testing the platform for accessing the data. So all of this has been processed using the standard LSST pipelines, and then some custom built DESC analysis pipelines of the data. But the other interesting thing is how are we going to get that data from LSST? And I think I'm slightly changing the tone here, because I'm going to talk about what data products are going to be accessible from LSST from the perspective of a user like DESC members. So the data in LSST that it's going to be acquired, it's going to be processed with this DIA pipeline every night, and actually candidates for transient candidates will be broadcasted in this alert stream within 60 seconds of being observed. So this almost real-time processing of the images is fundamental for brokers, for the community brokers, to produce prompt observations of interesting transients and to obtain the most of the information that you can get from these very rapidly decaying transients using the resources like SCORPIO or PESTO or many other spectroscopy follow-up facilities. So community brokers are central in filtering this huge alert stream and enable DESC, for instance, to select only the cosmology relevant transients and ignore variable stars or solar system objects. There's another period, which is 24 hours, in which the project, LSST project, will also produce a row or a group of rows in what is called the prompt products database. So after this 60-second period and through the first 24 hours of detection, multiple pieces of information are going to be available through this prompt products database. So it will contain, for instance, cross-matching with catalogs, for instance, to rule out every variable star that we know or solar system objects that we already know, and in this way produce more meaningful query results for the users. And finally, there's a kind of a not real-time release of data products. So basically, there's going to be multiple data releases from LSST project, which supposedly going to be happening once a year, in which again, members of the community are going to be able to access through the database, the products database. All of this is going to be done through what is called the LSST Science Platform, which is the specifically built platform to access all these three pieces of data set. So I'm going to talk about that later, but just to say once again, all the things that that LSST is going to be doing for us, for the community, after it takes the images. It's going to take the images, process them from raw state to calibrated images using the calibration frames. It's going to use external catalogs, and it's going to produce, with the use of the science pipelines, single visit images, co-added images, difference images, and not only that, it's going to detect objects and sources. It's going to run force photometry for us, and it's also going to do that for the difference image analysis. Lastly, it's going to cross-match with solar system objects, and it's going to produce alerts for the community to follow up. So this is all of what is in the project in charge of. So going deeper into what the time domain products database are going to prompt processing is going to be, again, it's going to be based on the difference image analysis. The DPDD, the data product definition document, specifies for LSST there's going to be two distinct different types of data that we can query: the DIA source and the DIA objects. The DIA sources are detections, as you can see here in the difference image, single detections. DIA objects are in turn groups of DIA sources, and actually groups of exactly one or more DIA sources. They are linked by coordinate. In this prompt products database, what we're going to find is all the information on historical data on the location of the DIA object, and we're going to find stamps, and we're going to find brightness and environment information. I think Emille gave them a much better representation of what the alert packages contain. Again, this is going to be processed by the brokers, And finally, there's this DIA source and DIA object catalogs being posted directly to the database, and it's going to be accessible through the LSST Science platform. On top of that, the data release is also going to be accessible through the platform. You can access to reprocessed DI source and DI object catalogs. This means that the project is also going to run subtractions once again, for instance, using better information on the templates, or using better information on the astrometry and so on. And it's going to have reprocessed images, for instance, single visits, improving the templates, improving the deep coads, improving the positions of the objects, proper motions. And this is all going to be available in the LSST Science platform again. So each data release will improve slightly the information that we have in sources. And finally, it's also going to be a place for people, for users, to generate data products with added value. So you can basically, as a user, use the LSST Science platform to combine different data sets and produce a new data product, something completely novel that other people can use and can employ in their analysis. So this is something that's going to improve the community access to all the information that LSST is going to measure for us. So very quickly, what is the Rubin Science platform? So I promised to talk about this also. So it's a set of integrated applications, web applications, that they are deployed at a data center. So basically, it serves out to the community analysis and visualization tools for the Rubin data products. And what's most important is this line here next to the data analysis of the Rubin data products. So this is an exciting piece of technology for the community to be able to access not only LSST data. So we're also going to see that there are external catalogs available in the RSP platform. It's split in three main aspects. The first aspect is called the portal, which is basically a tool for exploratory analysis and visualization of the LSST archive, but also not only the LSST archive. You can also connect to different databases, like I'm going to show you in a few minutes which ones. There's another aspect called the notebook aspect that runs plain and simple Jupyter notebooks, and it allows you to run in-depth analysis and also for creation of value-added data sets. These Jupyter notebooks are going to be running next to the data. So basically, you're querying on top of the machine that hosts this huge catalog from LSST. And finally, there's a web API aspect for remote access and integration of standard VO tools, standard virtual observatory tools. This API you can embed it in a website. You can embed it in an application and perform multiple actions on queries on the LSST archive using the standard International Virtual Observatory Alliance tools, like the astronomical data query language, for instance. If I have time, I don't know if I have time, I can just go quickly to run a quick tour of the RSP platform for people here.
Yeah, great.
Okay. So I hope you can see this is my web browser. So as you can see, I'm logged in, and just to be clear, this is this is a project that LSST DM is running, which is called the data previews. The data previews, or DP, are basically loading DC2 simulation from DESC in the RSP, in the Rubin Science platform. So what they have done is they have loaded all the truth catalogs and just for now, for the moment, the static science catalogs and measurements of DC2, this 300 square degree 5-year survey simulation, and is accessible for a certain amount of people who are testing this. So this will be called a beta testing in the industry of the platform. So As I said, we have 3 aspects. I'm going to go very quick to the API aspect. So as you can see, the API, let me zoom in so people. Okay, can you see well from there? So the API aspect shows you how to access data using the table access protocol. So if you have queried, for instance, the NASA extragalactic database or any other kind of survey database, you may have heard of this tap access. So you basically need a tap endpoint address like this one, and then you can basically run queries from every application, from any application, using the table access protocol. Some graphical interfaces like TopCat and PyVO or some libraries like PyVO also run on top of this, and they can serve the data for you to query. So this is rather simple. This is the smallest example. Let's go to the portal one. So if you go to the portal one, you're going to see it looks very familiar to some other databases like the IPAC database or the Mikulski archive. And actually, it's a very similar tool. You have a service which you're connecting to. So right now we're using the RSP. So this means that we're loading LSST data. We can also load any other TAP service that exists in the astronomical community. Like I mentioned, you can go to IPAC or IRSA. You can go to Gaia. You can load Mikulski archive images. You can load simulations in the GAVO. You can load extragalactic from the extragalactic database, and so on. So this is no different than many other tools available. You can do a single table analysis, just one table, query at a time, and you have this nice user interface, or you can run a more advanced query with the astronomical data query language. You can merge multiple tables and perform more complicated queries to the database. And there's multiple tables to choose from. So there are multiple schemas right now. You can, the data of the galaxies and all are in these DP0, DC2 catalogs. So basically, as it says, includes the 5 tables based on the DESC Data Challenge 2 simulation, 300 square degrees of the wide FASTIP LSST survey. And from that schema, we only have 5 interesting tables to us. The object, the truth match, so matching what has been measured and what has been simulated, the positions, the references in the coadded images, and then the force photometry in all the coadded images. So basically running photometry at every single detection. So I'm going to just run a simple query for you. It's going to be rather quick, but let's put 62, no, it's 67. I know what it's going to show, I think it's 34. And since I'm interested in the supernovae, we're going to just add a few constraints. We're going to require, as it says here, truth type to be 3, so equal to 3. We're going to stick to the low redshift part to get at least bright objects. And these are the coordinates. And then we're going to run a cone search, something very typical for us. Let's run a huge cone. And then, yeah, you can add a row limit. You can add multiple things in the different columns and all. But let's just run this. Oops, I forgot to mention that there's also a temporal field that you can fill with the MJDs or the MJD run range that you want to use. So basically, the results are going to be visible in the web browser for you to explore, but you can download the data, of course, and you can also extract the ADQL query for you just to put it inside your, let's say, Jupyter notebook or Python script, and build from that. Just nail down what you need in the preview, and then go back to the terminal or your code. Well, this is taking longer than expected, as it should be. I think I saved one of the queries. Let me see. No, deleted. Okay. Okay, I can just save time and go to the Rubin Jupyter aspect. So I have here a window with the Jupyter aspect already opened, showing only 2 notebooks. Can you see well? I hope you can see it well from here. Okay, it doesn't want to go full screen, but we're okay with it. So
if you could just shift a little bit the left-hand side. Yeah, right. Thanks.
Right. So let's do that. So as I said, this is all part of DP0, and I haven't mentioned that if you have data rights, you can definitely join DESC. And also, if you have data rights or expect to be having data rights by the time the survey is running, you can request for a DP0 delegate account. I think Mariano has one, Mariano. But you can basically request for this, and upon approval, you can play with this toy. This very neat toy of the Jupyter notebooks. So I realize it's very late over there, but I will just show a few things that can be done. The first thing is to mention that this is all done by Vera Rubin Observatory DM team workers. Melissa Graham, for instance. They've done an excellent job in making this available, and all these resources available to the DP0 community. So basically, I'm going to show the very basic bones. This is a notebook, typical notebook. It will run Python for you. It will import Python packages. So the classical NumPy, Matplotlib, Pandas. And it also includes the LSST libraries, which are central to query the dataset and produce more advanced analysis. So in this case here, I'm using something very important, which is the Butler. The Butler is basically the middleware interface to access the data. Butler, I'm not going to spend a long time explaining what it is, but it's basically an entity that can serve you with the data by request. Butler is built by 2 things: a registry, which can be a database, and then it's built by it's an object-oriented way of looking for the data. And it has an index. Yeah. So the main idea is that you can get the service, the TAP service, table access protocol, and you can query the results using a simple ADQL query. So you're selecting, for instance, the description or the table name from the tables that are in the schemas. And I rerun this, so you can see that all the catalogs that we were looking in the portal are here. You have the force photometry, the object, position, reference, and the truth match. And of course, you have all the schema information from the columns, the keys of the columns, and so on. So we can ask for the field names of the tables. We can ask for the descriptions of them. So this is very common in ADQL to explore the database using these simple queries. And also we can query a bunch of objects, coordinates and magnitudes from the object table. And the way to perform a cone search is using this contains function. So as in every Postgres database, SQL, database, you can have add-ons like in Postgres. You can define functions that actually perform indexing, search or searching by index. In this case, this is all indexed in the sky, and you can search using this contain function and defining points and defining a radius in the circle. So this query, for instance, will return all the objects. You're using the ICRS, so it means this right ascension and declination frame. You're giving the central values, basically the center of the cone, and then you're giving it radius in degrees. And then you're asking for a maximum number of records, and this is how you get some data. So in this introduction notebook, you can see more complicated queries, but basically it's doing whatever it's expected. It's retrieving the data from the database, and you can explore all the columns with this. Another neat thing is that it can also access to images. So you can look at the deep coads, or you can look at the single visits or calyxes. And the way it's done is through Butler. So the Butler is a different entity. The way to do this is it's not like ADQL, but instead it runs using something called repository, which is where the index of the Butler is. And then you have multiple collections inside a repository. Butler is being instantiated using these two pieces of information, and then you can basically perform multiple queries on different data sets for using Butler information. So it can get you the sky map, it can give you information on where things are located for a specific point in the sky, and it can give you something called the data ID. So the way the data is indexed in Butler is through this weird data ID that talks about tracks and patches in the sky. So it can basically return images, it can return whatever information is stored inside the LSST stack pipelines. So here you can see a very cherry-picked image by Melissa, which shows a very dense structure of galaxies over here. This is all in DC2 simulations. So the way you run this query, you just say to Butler, hey, get me the deep coad that is related to the I-band path and in distract and dispatch of the sky. And so you get the deep coad, and using the Matplotlib backend, but there's multiple backends that you can use. You can definitely plot this using LSST tools, IFW display, for instance, and you get the image. So this is an awesome tool. It performs very well. It can show you the masks from the reduction steps. It can show you catalogs that you can overlay on top of the images. You can create sky maps. You can use the PSF measurements and interpolate it in the image. So Butler will serve you all those pieces of data seamlessly. And then I think this is one of the main things to know about the LSST. It's going to be done like this in the way to access the data. And finally, I had another notebook from Melissa, which is trying to fill a very much requested feature of looking at SN1A in DC2. For the data previews, we don't have yet any time domain analysis, so it's all the static information right now, the coads only. So this is not yet possible using the DIA prompt data products. Instead, Melissa and Jeff Carlin have worked a way to find the photometry of a light curve, of a SN1A light curve. So the idea is to, again, use Butler and the standard LSST geometric query tools. You get the table access protocol and standard libraries from Python. Then you make your instance of Butler, giving the repo location, mentioning what collection are you referring to. There's multiple collections available. And then querying the table in the catalogs using the service, the TAP service, to search for supernovae. So it's basically selecting the coordinates and the IDs and the redshift of the truth match and using this center. So if you remember, I was running the very same query in the portal. I don't know if it ended. Oof, it failed. So let's go back. Let me see if we can do it. Let's put the truth match again. Equal 3, redshift 0.3, 3 degrees, 64, no, 62, yeah, 62, and minus 37. Okay, let's try again. Hopefully it will turn out better. Well, okay, this is obvious. It will fail. I'm sorry. But then the query should return the very same number of objects, the very same objects. So there's only one supernovae with redshift below 0.1. So we can get the light curve by using nice tricks from Butler and circumventing this not DIA information available. So the details are not very important, but the trick is that you can get the photometry for every image and run this collection of photometries of the very same location in the sky and get the supernovae light curve roughly. So I don't know if you have any questions. I might have went a few minutes, beyond the time limit, but yeah, this is basically the end. Yeah,
we have one question here.
Thank you, Bruno. Amazing talk and work, indeed. I'm not familiar with the database that you mentioned and the definition of the products, but do you know if it will be available by using, for instance, the Rubin Science platform, this database, or the products just will go directly to the brokers or are only accessible by the brokers?
So what I'm sure about is that the 60-second almost real-time information is going to be in the form of alerts. So basically, to read the alerts, you're going to be needing a broker system, basically. Let me stop sharing so you can see. So these prompt products, data products, are going to be accessible through the alert stream. So, and in order to read that alert stream and not collapse your machine, you need a broker. So, and these brokers are going to store the information that the alerts is containing by filtering and then keeping track of the historical information that each alert packet it's sending. Finally, there's this prompt products database. It's going to store independently rows with the information that has been emitted in the alerts. So there's been some discussion on how to match those and recover the information, because I think they expect that the prompt database is going to be updated with extra information besides what's in the alerts, in the real-time alerts. So at least the IDs are supposed to be maintained, and you can match these two things. The database is going to be accessible through the top service, as I showed. So the Rubin the RSP platform is going to be able to query that database. That's how I understand right now the status of things.
Okay, thank you so much, and thank you to the persons that are still here. Thank you so much for all the effort and the insight that you gave today.
Okay, thank you for organizing the workshop.
Do we have other questions? Okay, so let's thank again Bruno. Thank you so much to you and to all the speakers, and also thank to those that participants that could remain at the end. I know it was a very tough afternoon, but also was a very unique opportunity to have all the speakers together. So it's really great. A lot of information, useful, insightful information. So thank you very much. And well, of course, since Mariano's here, thank you for organizing this.
Yeah, thank you.
So
thank you, Mariano.
Have a good weekend. Goodbye.
Thank you all.